Right. Hello, hello, everybody. It is our happiness. We are glad that in this occasion we can continue with the day 2 of the Landslide Scientific Assessment Conference. Yesterday we had very excellent presentations, top scientific researchers presenting their already published papers in top journals. And oh, give me 1 sec. Today we are going to continue with the day 2 of this event. I am pleased to introduce to the speaker of today. We are having some 3 minutes to the people that is connecting, that is using or can find the links in the website. We are going to update the links because they were just created, the links for the streamings, both in YouTube and Facebook. So we take some minutes to update the links, to hold on, yeah, to wait for all the people that can follow us in this streaming, and exactly at the time that in your conference schedule here in Dublin. Well, I am right now in Castleblayney, very close to Dublin in Ireland. It is 1 p.m., but in the conference schedule, you can follow all the times in UTC. Yeah, so exactly at the time it was scheduled, we are starting this presentation. So today I have Dr. Yan Ji, a GIS-based tool probabilistic physical modeling and prediction of landslides. GIS form landslide susceptibility analysis is the title of his presentation. Hello, Dr. Yan Ji, how are you?
Hi. Hello, Rob2.
It is
Hello,
a pleasure.
Rob2, Dr. Marin.
We are very happy that you accepted this invitation, and it is a pleasure for all of us who are going to enjoy all the research you have done in this paper and on everything you are going to show us today. So thank you so much for accepting the invitation. You can, before starting with the thematic or what you have today, please tell us a little thing about what you do academically, about yeah, where are you right now, maybe an institution, and you can start with your presentation. Thank you so much.
Okay. Dr. Marin Roberto, thanks for your invitation to invite me to attend for this conference event. Today my talk is on the GIS-based tool for probabilistic physical modeling and prediction of landslides, of which the aim is to introduce GIS form landslide toolbox that developed by my research group. And before the presentation, give some little words about myself. My name is Jian Ji, and I'm a professor of geotechnical research, geotechnical engineering at the Hohai University in Nanjing City, China. And now I'm hold the professorship level position in my school, and my research is mainly focused on some aspects of geotechnical engineering, which includes the slope stability analysis, landslide susceptibility mapping, and also some some geotechnical reliability analysis with probabilistic modeling. So okay, that's just a little words about myself. I hope we can have some more chance to for some research or conference meeting at other place. So my topic actually for today is originated from a published paper that just in this year, earlier this year, we published our work on the journal Landslides, and this is the some details of our publication. I'm very glad to say that since the the online release of our paper, it has been attracting a lot of attentions worldwide, right? So for this paper, based on that paper, my topic for today is the contents of my topic will be some very some very summarized contents. I will give some research background. Let's look at China's geological hazards, status, current status. So 2 years ago, in 2020, there is the survey of geological hazards in China that happened summarized by the BRC, and a lot of geological disaster in China, because this is a map of China, and especially for some places in the middle or western parts of China, a lot of mountain areas. So geological hazards happen mostly on this area. And we have, as summarized or reported, figures said we have, 7,000, more than 7,000 geological disaster sites in that area, including many deaths and missing people, and also some of the injuries and economic loss, accounting for around 5 billion yuan in renminbi yuan. And this is the there's in recorded data of China geological disasters for the last decades, without any without any surprise. The landslide is the first place. Takes first place for the amount of disasters. So for the landslide, we have a better understanding that the most important triggering factors are earthquakes and extreme weather, like the rainfall, heavy rainfall, right? And the research interest on those aspects are continuing to increase in China and also worldwide. But for landslide prediction, the major objective is to produce some easy to follow or understand, easy to interpretation data or outputs, like the susceptibility assessment. We use the regional landslide susceptibility assessment for landslide planning or disaster mitigation, right? So, but for this work, the purpose is to roughly to estimate the failure probability for the region of interest. This is the actually what we call the landslide hazard susceptibility zoning map. I believe all the audience, most of our audience are experts in this field, so they are not, it's not common to understand. So, but for some basic concepts about the regional landslide hazard mapping is actually, well, we start with individual landslide analysis, which is typically known in geotechnical engineering for slope stability analysis. But for actually for slope stability analysis, that is a good topic, a very the most important topic in geotechnical engineering, and we have a lot of methods to do the slope stability analysis, like the linear equilibrium analysis, finite element analysis, and some others. But actually, for the landslide mapping for the regional area, it involves a lot of repeated calculations for that aspect, and we commonly adopt to some simple model like this is kind of an infinite slope model, which are sufficient for our landslide mapping, hazard mapping. And as for the regional landslides analysis, we except for the slope stability model, right? Except the stability model, easy to follow stability models. We also need some additional information like the geography, geological information, and even the regional rainfall data, right, etc. And as to say the regional landslides, the area is very wide, and it can involve a lot of unknown parameters, especially for the geotechnical parameter, right? Soil parameter, shear strength, soil shear strength, like rainfall, infiltration, etc. For those kind of geotechnical parameters, they are actually by nature show some uncertainty from site to site. So that is called the uncertainty of geotechnical parameters, which are important for our understanding, accurate understanding of the regional landslides. And the purpose of our work is to develop a probability analysis tool to predict the regional landslide failure probability. Right. For this, for that work, in the literature, we have two types of the methods, like the data-driven, right? Based on the data, historical data, we can regress some formula to be used for the regional and landslide mapping. And the second type is the physical modeling. Myself is also focused on physical modeling analysis. And I believe some other researchers, like some speakers in yesterday, the day one of our conference, and also Dr. Marin, yourself, right, is an expert in probability physical modeling. And the for the first type, the statistical regression analysis, they have some advantages like the rapid assessment, but it entirely relies on historical data. So by itself, it has some disadvantages, which include the lack of generality, because sometimes it can be overfitting method, and ignoring the intrinsic damage mechanism of landslides. And also it lacking analogous historical data or small data. If in this condition, our the landslide mapping could be not adaptable. So for the physical modeling, we can fully consider this stability model, right? A slope stability model, giving the geographical information, and we can take full account of real slope information, like this, and also the soil mechanical properties into account. And also versatile landslide mechanical analysis, we can include or we can adapt to different stability models. And a quantitative evaluation can be made for specific areas in the absence of historical data. So that is some advantages of the so-called probabilistic modeling, but also is subject to some disadvantages, unluckily, right? So like for example, for each cell, calculation cell or grid or in the region, right? We have to carry out individual slope stable analysis by the probabilistic modeling. And also for some large areas in the region, it can producing the hazard mapping could be time consuming if we use a very high resolution of the mapping, right? And the feasibility of probability phase modeling is that feasible for landslide mapping. So to do that work, we have to change the conventional way of the probability modeling using the geotechnical reliability method. So that's I'm sorry that the time is very fast, so I have to go a little bit quick of my research work, right? So and also the regional hazard prediction, we have some existing problems, right? Like we have some difficulty to implement the probabilistic methods. Yesterday, I think another researcher already presented his work based on the Monte Carlo simulation to account for the landslide mapping, accounting for soil uncertainties. And also there's some other alternative methods for the probability methods, like the first order first order reliability method, etc. So this is the focus of our work is to use the first order reliability method to produce the probabilistic realization or to produce the failure probability in the region, landslide region, right? So let's look at our developed tool, the so-called the GIS form toolbox for the which is based on GIS platform to produce or to realize the probabilistic physical modeling. Let's just look at a glance of have a glance over our method.
I want to tell you that you can have the time without any problem. One author, right. One author is not going to present, so you can take even more.
Okay, I thought I was giving only 15 minutes, but I need some time.
Ahead. Right? Yeah, one of the speakers canceled, so take your time.
Okay, then we'll take some time, additional time. Sorry. So for the geotechnical reliability methods that as a basis of our algorithm is so-called the first order reliability method for geotechnical reliability analysis. And this is the concept of probability of failure calculation. Actually, the purpose is to propagate the uncertainty of your input parameters to the results, right? The results can be the factor safety, mostly the factor safety for our landslide prediction. So for this purpose, we have the Monte Carlo simulation, right, method, as I just now briefly introduced, and also the some numerical methods, like the numerical method is to it's not to use the computer simulation, right, repeated simulation, but on the other hand, use some numerical tools to approximate the failure probability. And that is our work. And we developed a new concept for the iterative algorithm based on the HLF, Hasperlin Rankle Fissler, which is a sub-algorithm of the first order reliability. And we developed this iterative algorithm in the original space of random variables, resulting to our efficient algorithm called the HLF. X in the X space means the original random variable space. Either your random variable is in normal, log normal, or correlated log normal, etc. We can consider the full statistics over all the random variables, That is the advantage of our method. And we have some research basis and some previous publication on this topic. Interested readers, interested audience can refer to our work, previous work. And so regarding the implementation of the first order reliability methods in GIS platform, so this is the overview of the toolbox, how we develop our toolbox and the workflow, including the inputs by looking at the original DEM information, DEM, right? DEM, DEM information and the geological map, coefficient like soil coefficients, and some statistical information of the geotechnical parameters, and also we trying to use the parsing. It's called the NumPy integrated into with the ArcGIS. The output will be, by using our algorithm, the first order reliability algorithm, we can produce the reliability index instead of the failure probability. And then we convert the reliability index into the failure probability, which is the basis for hazard mapping, landslide hazard mapping. We can mapping for the factor safety, displacement, in terms of the seismic analysis, and also the failure probability of the regional landslides. And this is the algorithm flow chart, right, for the F1 first order reliability. And it roughly is based on iterative calculation, but the convergence is very fast, only 2 or 3 steps, iterative steps to achieve the converged results. So that is this is the toolbox interface, right? How we implement our methods and the inputs of all the necessary data, and also the choice of computational methods, and we can produce the reliability, or on the other hand, some failure probability to produce the hazard sensitivity hazard mapping, right? And the method including some we are knowing in terms of seismic analysis, we included some calculation models for the displacement, hazard displacements, assessment displacement, etc. And let's look at our method feasibility and some validation. So this is the inputs. As an example, we use some of the we consider some of the soil parameters to be on certain random variables. They follow some statistical distribution like normal distribution, or including the mean with the mean value and the standard deviations of each of the parameter, and also the statistical distribution. These usually are some basic basic information for the full stability, full statistics. And also some the stability model in terms of the factor safety formula. We use this formula, which was previously reported by another research group and published just last year. Right, this is the implementation, effective implementation results. We, for example, the landslide mapping, we consider those kind of this number of grid points, and the calculation time. The cost of the calculation is around 15 minutes. 15 minutes for this big number of grids. But I think this is a very sound, reasonable calculation cost. And here are some results, and we do some comparison between our proposed method GIS4 with literaturely reported method, so-called GIS-TESA. So by comparison between the proposed method and the others, we can say mostly for simple conditions, the results are very comparable. either in terms of the fatal safety or the some seismic acceleration for seismic earthquake based landslide analysis, and also for the hazard mapping. Hazard mapping, we are more interested in the failure probability, right? Failure probability for the simple working condition like the soil properties uncertainty, but just considered with very simple condition like independent of each other of the soil property, and also simply follow the normal distribution. The methods comparison, the comparison between our methods and the literature very agrees very well. So it proves our method is fundamentally correct and acceptable. And but for some complex working conditions, like if your soil parameters are correlated, some of the soil, like the soil shear strength, some of the soil strength, they have some correlation, right? So we consider correlation between the soil shear strength, and also we can consider the some non-normal distribution, like the log normal distribution, or some other beta distribution, or some other some complicated distributions, static distributions. In those complex working conditions, our proposed GIS form toolbox still works, but for the GIS Theresa, like some other simple reliability methods based platform or toolbox, they cannot do that work. So and also we show the effectiveness of our original landslide hazard mapping by the proposed GIS form. Those are example worked example, right? So the zoning, the level of zoning by differentiated the failure probability are shown here, right? Like our failure probability, the threat of failure probability, 5% or 10%, we corresponding to low failure probability, very low, medium, and high, etc. So the effect or the overall effects of the mapping, hazard mapping by the GIS form toolbox, it can, as shown in this figure, very interesting and sound results. Comparison by the two methods and are also shown here, which can say our method really can produce a little bit small failure probability compared with the first or the second moment. And this is the comparison between the two methods also in terms of the fatal safety, very good results, and each produce simply produce the same hazard mapping, because the fatal safety does not involve any uncertainty. So the two methods works equally good. And but for reliability index, which we may modeling the soil uncertainty and also the distribution correlation, etc. In this type, in this condition, our proposed GIS form looks better, right, than some existing simple reliability methods. And also the failure probability, the comparison between the failure probability, right? And this is the example landslide hazard mapping, and the resolution of this example, right, is 247,000 grid units, and the cost of the analysis is around also 15 minutes. So this let's also look at the case application. This is the real landslide events that taking place in 3 years ago or 4 years ago, right? In China, Judago, in magnitude 7 earthquake caused a landslide, the regional landslide in the area. And this is a data record, recorded the landslide size in that geological area. And here we have some reported data for the hazards, for the earthquake PGA, etc. Right, and also we have the local researchable information. And by that, from that literature, reported literature, we can assign the appropriate soil properties to each of the bedrock, different bedrock, and those are the parameters used for our analysis. And this slide roughly presents the specific mapping of the geological landslides. And also we show the influence. We present the influence of. We study the influence of the some parameters on the hazard mapping in terms of the failure probability, different probabilities. Right. We study the influence of the soil property variation in terms of the coefficient variation of the soil parameters. Right. They're corresponding to low, very low, medium, and high variation of the soil property. And we present the mapping, different mappings, comparison between the different mappings. Here is also a comparison between the mapping results. It's interesting to point out that the failure probability or in the mapping when you consider a higher coefficient variation for the soil properties, which is around 0.3 for the soil properties, and we can produce very good consistent results for the prediction and predicted failure probability, zoning failure probability, and also the observed between the observed true landslides events. And this is the POD curve made for the geological landslides. And we can, using the probability of the probability detection curve, we can quantitatively compare to study the soil property, soil shear strength variation, how the variation of the soil shear strength can affect our the probability detection curve. Or in other words, when your soil shear strength is around 0.3 of the coefficient variation, which is a reasonable number for the geotechnical in geotechnical engineering, then we can achieve a very good POD curve for our case study. And in the next few slides, we have some unpublished works, but due to the time limitation, we are not going to present all the details. So those will be the rainfall reduced modeling by the GIS form toolbox. And maybe I just jump to the conclusion of my presentation for today. So this study takes the probabilistic reliability algorithm driven by the physics model as a core, and which is embedded into the ArcGIS platform. And we can realize the rapid evaluation of regional landslides automatically and completed by considering some factors induced by earthquake and also the rainfall. But for this part, the latter part is still ongoing and unpublished work. And I think these results can provide a certain reference for the prediction and prevention of geological disasters. Using our developed toolbox, we can use that toolbox, very simple to easy to follow and easy to implement. We can achieve reasonable results for the original landslides mapping. And some reference of our work can interest the audience can look at our published work, previously published works. Okay, I think I have to end up my talk. Rob too. Hello.
Yeah.
Yeah, Rob too. I think I have to end up my talk today, and I'm glad to take any question.
Yeah. Thank you so much. Yes, as you know, we invite you to write all your comments via Facebook or YouTube. I am checking right now. I think I have just one comment or question. And here it is. What was the vertical depth of landslide by 7 magnitude earthquake in China in your study area?
Yeah, the earthquake induced, a landslide in China, right? So I think this is a very important topic that currently under investigation, and also we are we did a lot of work and some preliminary analysis for some events, seismic landslide events. Actually we have some data, right? We can collect some data from the bureau in China some earthquake bureau. We can for some real case studies and landslides. We have lots of different groups of researchers who work on that topic. For us, we just present our work for just when typical recent landslide in the events, right? And also I want to highlight that our work, the kind of work is very effective for the earthquake-induced landslide mapping. As for the rainfall modeling, rainfall in events, we also have did a lot of some preliminary work, and we can integrate our GIS-form toolbox into the triggers model, right? And also your Rob 2 is also work on the triggers modeling, right? Yeah, for the rainfall induced landslide, and we are also moving on that direction. But we just trying to produce the integrated first order reliability method for the rapid landslide mapping for the rainfall events.
All right. Thank you so much. Thank you for your great presentation. We don't have more questions, right?
Okay.
As I told before, we had an unexpected problem with a speaker that had problems with his health. We apologize and we are very sorry for that, but of course his health is more important. But he sent something, but I apologize with the next presenters, but yeah, we can continue right now. It is, let me check the time because it is 12:36 in UTC time, right? Then we have Sandeep Panchal. It is an honor for us to be with you today. The title of the research paper that he published is landslide hazard assessment using analytic hierarchy process, a case study of National Highway 5 in India. So it is an honor for us to have him presenting this research paper, and also we invite you all who are attending this uh, conference to share the link to download the papers that you can find in the uh, web page of the conference. We have the DOI or the links of the papers there. So if you find them interesting, of course, we invite you to read the papers. And hello, Sandeep, how are you?
Hello, Roberto. I am fine. Thank you for the invitation. I hope I am audible.
That's great. It is an honor for us also that you are here.
Shall I begin?
Yeah, you can begin. Remember that there are any problems with the time, because as I told before, we will have
Okay.
time. But also, please, before you start talking about the research, we want that every speaker tell us something about himself. It can be where are you in the academic world, if you are in an institution, and where do you, and then you can go with your presentation. You're very welcome.
Thank you. I have recently I have finished my PhD from Delhi Technological University, India. And my work is on landslide susceptibility and landslide hazard mapping in Indian continent in Himalayas. Currently, I am working as lecturer in Department of Technical Education, Government of Uttar Pradesh, India. So sharing my screen. I hope my screen is visible.
Yes, it is.
So good evening, ladies and gentlemen. Our work is on landslide hazard assessment using analytic hierarchy process. And we have implemented this along National Highway 5 for a particular stretch that lies from 197.600 kilometer to 283.200 kilometer. This is my PhD work, and it is a part of my PhD work. However, we have implemented other techniques for landslide hazard assessment in India too. But this paper is all about implementation of AHP, analytic hierarchy process only, along the highways. So these are the contents. We will begin with the introduction and objectives of the study. After that, go to the study area, literature review, what kind of methodology we have adopted, the different causative factors, and after that, how we performed this study along the highways. We know that crucial the hilly regions are developed at a very rapid rate in Indian continent. So there are numerous construction activities, the upgradation of highways, and many anthropogenic activities are taking place. That's why the slopes along the highways has become unstable due to these construction activities and anthropogenic activities that have been conducted. So there is a lot of human interference along the highways and even in all the hilly regions, because they have started developing from last 2-3 decades only. So that's why the infrastructure is growing. But as the infrastructure is growing, there is disturbance in the natural slope. That's why the number of landslide events have been significantly increased in the hilly regions in India. So the planning and management of landslides along highways is very important. Whenever a new highway is proposed or an existing highway is upgraded from for more lanes or for more width, at that situation, the landslide planning is very important for the hilly regions. So that's why landslide susceptibility maps and landslide hazard maps are one of the very efficient tools in predicting, planning, and management of the landslide hazard. With a small definition of landslide susceptibility maps that is given by Geological Survey of India, Geological Survey of Ireland, that it identifies the areas which are subject to landslides and is measured from low to high. So the objective of our study there are only two objectives: that we wanted to identify the causative factors of the landslide. This can be done by the literature, the available literature, or by the field visits. And second, we attempted to prepare a landslide hazard map along the proportion of National Highway 5 in India, in Shimla. So let's talk about the study area. Our study area was National Highway 5 and the stretch of a national highway. And it is situated in Himachal Pradesh, in Shimla and Solan districts. While National Highway is a long highway, it is around 600 kilometers long, but all the complete stretch don't go through the hilly region. That's why we have selected only the part that goes through the hilly region, and that is from 197 kilometers to 283 kilometers along the National Highway 5. The longitude and latitude of the study area are given here, and it lies in that. And the elevation of the study area, there is a very high variation in the elevation. The elevation from the mean sea level varies from 591 meter to 2459 meter. And the temperature of the study area also varies significantly, like 6.2 degrees Celsius to 36.7 degrees Celsius. However, even this is the average temperature, the variation of average temperature. However, in winter season, it goes near about, the minimum temperature goes near about 0 degree and all. So it is a crucial region, as Shimla, our study area, is the capital of Himachal Pradesh, that is a province in India. So it is very important according to economic point of view and socially. So we have separated our study area. We have extracted our study area. Here, the first map shows the map of India, and here lies the Himachal Pradesh province, where our study area is situated. In Himachal Pradesh, these are the various districts. Our road that is along which we are conducting the study lies here. That is part of Solan district and Shimla district. And the elevation is shown with various color combinations. So before selecting the analytic hierarchy process for this study, we have gone through some literature, and the techniques for landslide hazard assessment and landslide susceptibility mapping in GIS environment and are basically divided into three parts. The first type of methods that are used are qualitative techniques. Second one are quantitative techniques, and another one is semi-qualitative or semi-quantitative techniques. The qualitative techniques are based on the decision of the expert, where the expert suggests the contribution of various causative factors in occurrence of landslide according to their wisdom. So qualitative techniques are purely expert-based techniques. In this, the evaluator selects the relative importance of causative factor. So these are very simple to implement normally, as these are based on the judgment of the expert at that situation. We don't need landslide data. I mean, if the landslide data is not available for a particular area, then it is all right. We can go for the expert weightage, and they will not be requiring any landslide inventory. If it is available, it is good. It will help in taking the decisions by the expert, but otherwise, it is not mandatory for this. But the problem in the qualitative method is that the first, it completely depends on the subjective judgment of the expert. So the judgment of the experts can vary from expert to expert, depending on their experience. So that's why it don't give much accurate results. And even the accuracy of such techniques can't be evaluated if the landslide inventory is not available. So second one are the quantitative techniques. The quantitative techniques uses the mathematical relationship between occurrence of landslides and the causative factors. So various statistical and mathematical models that are available for landslide susceptibility mapping comes under category of quantitative techniques. So these methods depends on the spatial distribution of landslides. So the one thing that is important for implementation of quantitative techniques is that for accurate result, we will be requiring a very well distributed landslide inventory. Means I should have the historical landslide data. Only then we will be able to implement the quantitative or mathematical models, as these develop the relationship between occurrence of landslides and the various causative factors of landslide. So these two techniques are widely used by various researchers, and this one more, there is other technique too, that is semi-quantitative technique or semi-qualitative technique. It is a kind of hybrid technique where the expert opinion is used, but it is restricted by some mathematical model, means some validation is taken by the mathematical equations and all. So with the help of some mathematical relationship and the opinion of expert, we can predict the occurrence of landslide, or we can predict the landslide susceptibility. Such techniques comes under category of semi-quantitative techniques. Now in our study area, whenever this work was conducted, so it was difficult to conduct the field work. At the time of COVID, we were not able to make frequent visit to the study area, and we were unable to take the data for landslide inventory. This was the case one. Second, we can use the Google Earth data for preparation of inventory, but still this data should be validated with the ground stations, and we were unable to do that due to the restriction in movement. That's why we selected a semi-quantitative technique, and in semi-quantitative technique we selected the analytic hierarchy process for this study. And in analytic hierarchy process, in simple words, we break the problems into the criteria, and these criteria are given weightages according to their relative importance, and then the ranking of the criteria is evaluated. Once the ranking of the criteria is evaluated, we can overlay them with that weightage, and we can get the landslide susceptibility or landslide hazard map. So this is a scale that was given by Thomas L. Satie in 1980, and it shows that how we compare the criteria. If in a pairwise comparison matrix I give value 1 to 2 criteria, then it means that both the criteria are equally important. If one criteria get value 3, it means that one factor is more effective as compared to the other factor, and so on. And similarly, the intermediate values are also possible. So this is our table. This table shows the pairwise comparison of various factors that are considered in this study. In this study, we have considered around 9 factors, and the first causative factor that is considered in this study is slope gradient. Slope gradient is divided into 5 categories as shown in the table, and the pairwise comparison is shown for the various subcategories of the slope gradient. And according to AHP, it is found that the slope gradient that was 45 to 60 degree has a weightage of 0.262. Its contribution is high, and as the slope gradient is increasing, its contribution towards occurrence of landslide is increasing in this particular area. So this is based on the expert weightage, or the perception of weightage, perception of experts. Similarly, the second causative factor is the aspect, and we have compared the various aspects, and we have prepared the weightage according to AHP. There is a term consistency ratio. The consistency ratio is the restriction that makes this method the semi-qualitative or semi-quantitative method. The consistency ratio restricts the values, like if the consistency ratio is more than 10%, then in analytic hierarchy process, it is considered that the weightage given by the expert are inconsistent and the input can be varied. Means the input can be varied and the values can be changed to get the better consistency ratio. So in this process, we have maintained the consistency ratio below 10%. So similarly, we have other factor like curvature. It is seen that the concave type of curvature were more susceptible to the landslides. The relative relief varies from 0 to 254 meter, and again the weightages are given. The geology of the area has a wide variety of geology, and there are various groups of soils that are encountered in the study area and are weighted. Similarly, the lithology is considered the another causative factors of landslide. And fault density is the another one. So we have considered 9 factors for preparation of landslide susceptibility map. We have prepared the pairwise comparison matrix. We have compared them and got the numerical index with the help of analytic hierarchy process. This was our methodology, that the slope, aspect, curvature, relative relief, and topographic wetness index is extracted from Ester DEM. From DEM, we have extracted this data. The landslide inventory, however, validated from the field data. We visited the field and performed our studies, but lot of data is taken from Google Earth too. And with this combination, we have prepared the landslide inventory. Here in India, there is an agency, that Survey of India. We obtained these maps from Survey of India, and after that we have digitized these maps in GIS environment. Now, taking this all data, we have assigned the weightage according to analytic hierarchy process, keeping the consistency ratio less than 10%. And with help of AHP, we assigned the weightage to the causative factors and prepared the landslide hazard map. And then landslide hazard map is validated using area under curve and receiver operation characteristics curve characteristics. So these are the inputs that have been calculated in the study. The first one is the slope map along the national highway. We have taken a buffer of 1 kilometer each side of the highway, and up to that we have prepared the hazard map. So these are the various inputs that are calculated. So here is the geology map, relative relief map, lithology map, fault density, drainage density, topographic wetness index, and distance from road. Distance from road is the most important parameter as we are studying the landslide susceptibility along the highways. It is seen that whenever the highways are constructed in this study area, when this particular highway, National Highway 5, was constructed, the bottom portion of the slopes was gone through a huge cutting activity. So it was cut. That's why the toe of the slide has become unstable, and the overturning problem is there. So that's why we consider this factor. And as we reach near the road, the slopes are more prone towards landslide in this particular study area. So using AHP and after implementation, we also compared the various major causative factor too, and we received this kind of weightage for the study area. that the contribution of slope was this, for aspect was this, and so on. So each numerical weightage shows the contribution of each causative factor, and the contribution of sub-factors is shown in the table above. So the landslide hazard index for our study area is based on this equation, and the landslide hazard index varies from 0.0783 and to 0.576. It is found that 40% of the study area lies under very high susceptibility, while 23% of the region lies under high susceptibility. So this is our final map that shows the landslide hazard or the landslide susceptibility of the region. The landslide data is shown with dots. The red color shows the landslide testing data, and blue color shows the landslide training data. It has been zoomed, otherwise it will not be visible on such kind of map. So this is the final output, and based on this, we gave the results that how much area is susceptible towards landslide and how much is not. So we tested the work, we tested the accuracy of this output on the receiver operation characteristic curve, and it was observed that the accuracy was quite good. But the accuracy completely depends on the available landslide data. So moderately, it was quite accurate. So these are the conclusions. We have used 10 causative factors, and we had a data of 215 landslides, and 70% of the landslide data was used for training and 30% was used for testing purpose. And the landslide hazard map was divided into 4 zones, and the output is calculated. So in case of analytic hierarchy process, there is the only problem is that that again it consider the opinion of expert, and we check its consistency, but there is an opinion of expert which may be subjective. Secondly, if a good landslide inventory is available, then more accurate results can be predicted. The statistical models we have observed from the literature are very accurate if the historical data is available, and the expert-based models have somewhat not that good kind of performance in case of that are purely based on the expert opinion. So this work is published in Ancient Engineering Journal this year only. It was published in like 2022 in the edition of May. And our few other works are also published that evaluates the statistical model in landslide susceptibility mapping too. So that's it from my side. So that's any question are welcome, Roberto.
Yeah, all right. Thank you so much. Thank you for your excellent presentation.
Thank you, Roberto.
Let me check. It occurred in the past that I missed some of the question because the streaming takes like 30 seconds, but here are some questions. What is the difference between geology and lithology map?
Sir, actually, geology is the type of soil that is considered various soil groups that are in the study area, and lithology are the rock groups that are available in the study area.
All right. And what is the difference of landslide susceptibility and hazard mapping?
Actually, in landslide susceptibility, we don't consider the time frame. So we have taken here only the monsoon data. So that's why it is the landslide hazard assessment for the particular highway.
All right. Is there any other questions? I just write them. I think we don't have more questions right now. So thank you so much, Dr. Sandeep Panchal.
Thank you,
Congratulations
sir.
for your research advancements, and I'm sure you'll continue publishing and giving to all of the researchers and scientific community excellent research results. So maybe one day we will have you again. So thank you and blessings.
Sure, sir. Thank you. Thank you very much for the invitation.
All right. It is 1 p.m. in time in UTC. We are happy again to be with all of you. As we told you before, and we are sorry with the news of Dr. Janik theory about that he's sick. He tried very hard to be here, even some minutes, or yes, even minutes ago, he wrote me the last email and told me that because of his condition right now, he could not be here. But even he sent me a presentation. He proposed that if I would at least show the presentation, and if maybe any questions or things about it he would be happy to answer. It is the first time, of course, it is the first time we have a conference as organizers. So also the first time we have this particular case, but it is okay for me. I can, right now, let me see the conference schedule. I am going to take some minutes to share with you the material prepared by Dr. Janik theory, and then we can if there are interventions or comments or anything that all the attendants want to share with us, we can read them. And I think it is something we can do. I have a PDF document here. Let me see how I can, yeah, how about a full screen. So in this moment, I want to say hello to all of the people that is getting here connecting to the streaming, and we invite you to check in the conference website all the info of the event. I received many emails from people with different things. Even some of them told me that they did not receive the links of the streaming as I shared in the previous email. We invite you to subscribe to the YouTube channel or on the Facebook page, because you will find it immediately when we start the streaming. I have to copy the link, to send the link, to right now 870 registered participants. It is not so easy. I have to do it in not in just one email, and there are restrictions to send massive emails, things like that. So I invite you to be following the channels, or the channel and the Facebook page, if you as you prefer. All right, I am going to share line now. Give me 1 second. I find all right. Of course, it is not my research work. It is not my presentation. I am going to just show this very interesting material. What was done by Dr. Yannick Thierry. He even include the co-authors and other researchers that worked with him. Their last names are Colas, Grandjean, Macquarie, Pressard, Gardier, Bernardi, Perisito, Levi. I'm sorry if this is not the right pronunciation. Right. The title is Quantitative Landslide Hazard Mapping in France towards an estimate scale approach. I am going to just share the presentation. You can look at what they prepared, including more than 700 engineers and researchers. And it is impressive how the French Geological Survey is working right now. So congratulations for all the work they are doing. You can read why they are directing, what they are trying to do or doing there. There are the activities that they are sharing with us for this presentation: scientific research, support for public policy, mining security, research and development for private companies, international cooperation, education and training. That's great. He also prepared this geology, groundwater management. All right. Of course, it would be awesome that the same author would present those slides, but yeah, at least we can have the material he prepared. As I told you before, Dr. Yannick Thierry is sadly he's sick, so I hope him to recover from his sickness. All right, I think these are the regions that they cover in France, all over their territory. here very interesting numbers and data about what they do. If you want to share your comments, if you want to ask questions, even if Dr. Janik Theory is not here right now, he invited us that he would answer all those questions when he gets better. Here's some contents: Landslide semantics, notions. Landslide has hierarchies mapping in a regulatory framework for brands. You can check the contents of the presentations he had prepared. Landslides, probably a definition. Displacement of a mass of materials down a slope along a surface failure, principally due to the gravity. We can look at those pictures of landslides that occur in France. It's a complex phenomena with predisposing factors and triggering factors. Some catastrophes that occurred in France. Fortunately, many casualties due to those landslides. Also, he presented numbers about the costs of landslides in France. Yeah, it is a very interesting presentation. I think, if I remember, he allowed us to check it. I don't remember. I have to read the email again if it was to be shared with all of you. You can. We will find a way to share it with all of you. Oh, sorry. It's private. I think it was not going to occur. Sorry. Yeah. I think it is not the idea that I talk about the presentation completely. So I am going to show some of those things. Then we will have the time to see all about what they did in their research work. Probably as I have this idea for other future small conferences. I mean, probably each month we are thinking to invite just one research author and have not a whole day with presentations, but monthly to have a different research author presenting just one paper, just a 1 hour presentation, and each month to have recent research papers published and allow all the landslide researchers to check and know what are doing the other researchers worldwide. This is one idea, so maybe one of those that can present would be the Dr. Yannick theory. We are very grateful with his intention to be with us, to prepare this presentation. Sadly, he is sick and he was unable to be here. It is a shame for all of us. Yeah, he did same conclusion. I am going to verify as he told us, as I think he told me in the email, I was able to share the presentation, the document to all of you. So the idea is that you can check the presentation and then any question, comments, he will attend without any problem. And yeah, it is a wonderful invitation. The 14th International Symposium on Landslides, 18th to 12th July 2024 in Chambéry, France. I didn't know that. Many of us attended to the previous International Symposium on Landslides. It is a magnificent event. It is something amazing. I also have to invite you to the World Landslide Forum next year in Florence, Italy. These are wonderful opportunities to learn, to share with other experts, or learn from the top scientific researchers on landslides. So yeah, it is that invitation. I want to publicly say to Yannick Thierry that we support all what he's facing now. We could say it is a shame that he was not able to be here, but his health is way more important. So I will even have him in my prayers that he may recover without any problem. I hope he will get better to recover completely. All right, I'm going to stop sharing. I am going to stop sharing in 5 seconds. All right. Yeah, then we have some time to have some announcements, to have a break. I have to, as I told you before, it is a very important challenge for us as organizers of the Landslide Scientific Assessment Conference to prepare all what we prepare. We are not a institution or a university. We are just that can invest money for those things. We just decided to do something that we think could be valuable for the scientific community, for hazard managers, students, professors worldwide, because maybe you have the same purpose we have. It is to save lives. The purpose of doing research for me is saving lives from natural hazards, disasters, and yeah, it was an opportunity to allow all of us to receive the knowledge directly from top research authors presenting their research papers. So you can't imagine that planning this event, of course, we made an incredibly big effort, but also it occurred that the dates of the event finally coincided with the time where I was going to arrive to Dublin. I just moved to Dublin, so it was incredible to plan all what is moving with my wife to a new place, and also to the same day be with all of you here. So this is what I want, some of the things I want to tell you. So, all right, we are going to have a break. I am going to say also, let me check the conference schedule. All right, we are going to continue at 14:30 UTC time. So again, please, if you want, go to the website of the conference, find there all the info that is required, that is needed, you want to have. Also, we have today a discussion section. Let me check what time was it. All right, 17:05. Today we are going to have, even if it is just 40 minutes, we are going to have this discussion section. So please go to the conference website and find probably just two links where we can decide what topic we can interact to discuss with the other researchers or people. So it is allowed to all the participants. So you can find the links. At first point, I thought it was going to be Zoom, but for the discussion section, we decided it was going to be easier to use Meet. So it is going to be a link for you can be with us in Meet. So go to it is landscient.com/conference, or in landscient.com you can get to the link, but I know many of you have the link of the conference website, so yeah, we invite you to go there. So all right, we will see you after this break. All right. Hello. Hello, everybody again. We are waiting some seconds. I know the people is going to come back to the streaming. We have had one day and some hours of the second day of great research papers presented by the same authors, and we are going to continue today with other wonderful research paper. I am talking about the paper published by Dr. Vitos entitled A Thermo-Hydromechanical Approach to Soil Slope Stability Under Climate Change. So we invite you to download the paper. We share the link of the research paper. So, but we have the privilege or the opportunity. We are very honored to have Dr. Vitos today with us. How are you, Doctor? Hello.
Hi, Roberto. Hi, everyone. No, it's a nice day today, and it's nice to be here. Thank you. I'm fine. And I am ready to explain everything to you.
That's wonderful, right? Go ahead. You can start right now. As I asked to the other speakers, we want that you present yourself. You may can tell us about where are you working right now, what are you doing, and then you can start, please.
Of course. So, again, hello everyone, wherever you are in the world. I am Vitos, and yes, today I'm going to present a work and its background. Actually, it's a work that was presented that was published in Geomorphology. I work at Charles University in the Czech Republic. And I am there an assistant professor, but I'm actually from Italy, and where I did my master and my PhD in geotechnical engineering. After that, after my PhD, I spent a couple of years in China for a postdoc focusing on landslides, in particular on earthquake-induced landslides. In Prague, in Czech Republic, instead, my work is concerning more the thermal aspect of the behavior of the geomechanical, of the behavior of geomaterials. So I shall get started by saying that, and by acknowledging funding from the European Union for this project that involves me and Marco Locke, who is also from Italy and is a PhD student, almost finishing his PhD with me in Prague, Czech Republic. So why a thermo-hydromechanical approach to soil slope stability, and why this reference to climate change? Let's try to understand with a bit of background. First of all, why thermal geomechanics? Now, why this subject? I advocate for establishing thermal geomechanics, so thermal soil mechanics, thermal rock mechanics, as a specific branch, a specific direction of research, and if you want, even a specific subject to teach at university, by collecting and structuring in an organic way, this is my work now, all problems that can occur in nature or in engineering, in which the knowledge of temperature dependent or thermally activated processes is crucial. And in fact, there are many applications, some that are in a bit more advanced stage, and some other are just starting to appear in the literature. One of the applications which are more advanced in terms of development is the use of thermal geomechanics in deep geological repositories of radioactive waste. But also there are applications in geothermal piles or in shallow geothermal pumps in general. And then that's what I'm trying to develop more in the study of the stability of slopes in various climates, in various conditions. So from rock slopes at high elevation that are threatened by ice melting, down to more gentle slopes and the hill slopes that can be overheated by wildfire in terms of very shallow cover, or progressively over a long time by global warming. My paper, our paper in geomorphology is a review paper, so that's why I'm talking more about the work done by others to set a scene, to set a starting point for my own research and for future research. And in fact, progress in science is often made because there is some need, because a need arises, and this need is often very practical. There are very practical motivations that motivate, that trigger certain studies. And the first studies on thermohydromechanical, THM, behavior of geomaterials in engineering or engineering geology date back to the 1960s. A pioneering report commissioned by the US Highway Research Board was prepared that time by Professor Jim Mitchell, that I think many of us know for his achievement and for his handbook, Fundamentals of Soil Behavior. He collected and discussed 14 papers in the 60s, focusing on various aspects of temperature and heat effects on the mechanical properties of soils. In his case, there was a practical issues in transportation, in geotechnical engineering in transportation, because the newly built soil road embankments in very arid and hot areas in the west of the United States would get damaged. And so they would try to understand whether this damage of this embankment was caused by the extreme variation in temperature during day and night or over the season. So this was really a pioneering report, and it collected really interesting insights on the thermohydromechanical behavior of soils in particular. So one of these studies that I like particularly shows how a normally consolidated clay, in this case it's a remolded sample of illite, can shrink when it's heated during consolidation. These are it's a consolidation phase of a sample. The material was normally consolidated, I think, down to 200 kilopascal, then maintaining the stresses constant. Simply, it was heated, it was warmed up from 18 to 59 degrees and then down and up and down again. So the soil would shrink upon heating and swell upon cooling, even though this may seem counterintuitive. And the process was repeated cyclically, and it was shown to be partly plastic, so with the irrecoverable deformation at the beginning in the first cycle, and then it turned out to be fully elastic. But what is interesting is that by heating and cooling a clay soils, you could obtain an overconsolidation, and apparently it's not a real overconsolidation in mechanical terms, but the volumetric response is exactly that. Heating and cooling would cause the same shrinkage, the same consolidation that could be caused by a loading-unloading cycles. And of course, upon further loading, this would result in stiffening. So the material, which is heated and cooled, would settle and become very stiff at a certain point, that you need a much larger load to produce other deformation. So by heating and cooling a material, you can actually get some benefits in terms of mechanical response. There is also a corollary to this, because if you sample a soil in the field and you find out that it's over-consolidated. Let's say that the over-consolidation ratio of a soil that you sample in the field is 2. Now, this over-consolidation, you would think that it's because of a mechanical over-consolidation, but that is not sure. An over-consolidation of 2 could have been obtained simply by heating and cooling, by natural heating and cooling of a normally consolidated soil. So that tells you that even when you think you have the answer, maybe that answer is not mechanical, maybe it's thermal. Now, broadening a little bit and focusing in particular on saturated soil, in general, thermally induced volume changes depend on 2 things, basically. They depend on the different thermal expansion coefficient of the minerals composing the aggregates, let's say, in the soil, and water. Typically, the thermal expansion of water is way larger, it's way greater than that of the individual mineral. But that depends, that effect depends on whether the soil has an open structure or a closed structure, because if the soil has an open structure and the water is expanding in the pore, maybe these aggregates that are in contact, they may lose contact, they may detach, and so that you can have a collapse. So that's why in a normally consolidated material, when you heat the water expands and the structure actually collapses and the water is expelled. But particularly in clay, there is also another effect that is related to the physico-chemical interaction on the clay mineral surfaces. So it's a microstructural effect. And this microstructural effect in clays is actually what typically dominates the entire thermal sensitivity of a clay-rich soil. And that happens because the water absorption capacity of clay minerals is really strongly influenced by temperature, and the roots are in the chemistry, in the thermodynamics of the microscopic processes. It's there that really a lot can change in terms of chemical bonds, hydrogen bonds, because these bonds can get broken at high temperature, can get stretched, and water can escape from the surface of the clays that can actually dehydrate at high temperature, again shrinking the entire microstructure. Now, this picture, this volume change behavior, so that described this way phenomenologically in the 60s, actually is valid if we assume fully drained condition. But if the change in temperature is rapid compared to the ability of the soil to deform volumetrically by expelling or sucking up water. So it's actually a competition between the thermal forcing and the hydraulic conductivity of the soil. Well, the response to thermal forcing may be undrained, or at least partially undrained. And if the response is undrained, what we get is a thermal pressurization. If we are heating a normally consolidated soil, the soil wants to shrink, but the permeability is really low. Well, we have a time in which there are high pore water pressure, and we get consolidation, exactly like a hydromechanical consolidation, because of the progressive dissipation of pore water pressure excess. This pressurization is bigger, is larger if the material is stiffer. So you see this on this MV and MW. These are compressibility, volumetric compressibility of the water and the solid skeleton. And the smaller is the compressibility, the larger will be the pore water pressure response. It can be calculated that a change in undrained condition of just 1 degree Celsius can cause a change in pore water pressure in the order of 1.5%. Now, this seems tiny if seen like that, but now consider a situation in which you have already an active landslide. Consider a slow-moving, creeping landslide that is moving continuously, and maybe it has a seasonal acceleration. This landslide has a factor of safety that is basically 1 or very close to 1, or it gets 1 when there is a remobilization, a fast period. This is a case study that it actually does not involve temperature. It involves changes in pore water pressure, but I show this as an analogy. So think that in this case of a clay landslide, we have seasonal changes in pore water pressure. This is deep-seated, so it's deep pore water pressure. They don't change much because of the surface rainfall if there are no discontinuities that really communicate hydraulically with the shear zone. But anyway, you have changes in pore water pressure in this case study in the order of 3% between summer and winter, between rainy and dry season. This 3% causes changes in safety factor in the order of 3%, but in terms of movement, these are deep displacement evaluated with inclinometer. You have accelerations during the active season of the landslide by 1 order of magnitude or more, meaning that a 3% loss in factor of safety makes the landslide 10 times faster. Now consider that a 3% decrease in safety factor can be caused also just by an increase in temperature of 2 degrees. And 2 degrees warming at a certain depth in the underground is very likely between summer and winter. So you can consider that there might be in the world landslides that are remobilized or accelerate because the ground is getting warmer and the soil is weakening, or it's pressurizing. No? Of course, this is hypothetical, but as a mechanism, it's perfectly possible. 2 degrees change over the season in a very low permeability material, it's actually partially undrained, because in a very low permeability clay, it may take years to dissipate pore water pressure excess. So it's perfectly reasonable. Now, this is a mechanism that actually involves volumetrically induced thermal pressurization, let's say. But besides that, experiments show a direct thermomechanical mechanism, sorry for the wordplay, which occurs also in drain condition. And most publications available now in the literature indicate generically a decrease in strength with temperature increasing. So warmer temperature make the soil weaker and more prone to landsliding, more prone to reactivation as well. But the actual situation, to say, it's a bit or maybe a lot more complicated than this. And in fact, if we just take the peak shear strength, this is a very nice work again from the 60s, from that famous report. The peak shear strength is influenced both by the temperature during shearing and the temperature during consolidation. So you can get a pronounced peak with a post-peak decay also in soil that are consolidated at high temperature, but then they are sheared at low temperature. Imagine a soil that is subject to hot summer temperatures, and then it fails as a landslide during the winter. The behavior will be strongly like an over-consolidated material, in fact, exhibiting a high peak and a post-peak softening. And that's because of the different thermal condition during consolidation and shearing. But in general, if you look at the picture, on the horizontal axis, you have the reciprocal of the absolute temperature. Here you can get the actual temperature, on the right, low temperature, on the left, high temperature. And these lines, they are sloping towards the left, meaning that at a given temperature of consolidation, the peak strength decreases with increasing temperature of shearing. So if you have a consolidation at a certain temperature, no matter what, if shearing or if failure occurs at higher temperature, the peak will be lower. So actually, failure should be easier. Very interesting result, but let's move on from the peak to the post-peak to the residual shear strength. This is a much newer study, just a few years old, which we actually dissected, and we are repeating certain experiments to understand whether there is really a strong pattern, if they are repeatable on many materials. This group of scholars from Kyoto University, in fact, they published in Geophysical Research Letters and in JGR, the AGU journals, evaluated the residual shear strength of a natural clay on the left. This is a natural clay containing smectite, and on the right, they used a commercial calcium bentonite to better evaluate the behavior on a pure material. They made ring shear tests at different temperature. In particular, black line here shows tests conducted at room temperature, 20 degrees, 22 degrees in their case. They did it when it was warm in the lab. But then they cool down all the experiment. Normally, you cool down the water bath that is saturating and the circulating bath that it's around, that surrounds the samples. And in this way, you cool down also the sample that is inside. They cooled it down to +7 degrees Celsius. They did not freeze the soil. They just cooled it down to simulate autumn conditions, for example, in the slopes of this area in Japan. And what they noticed was an over 10-15% decrease in the shear strength, over 1 degree loss in residual friction angle, that for a slope that is already unstable really can make a big difference, can remobilize, can speed up an existing landslide. They did the same for a commercial soil. They also went into warming, and they say that the colder is the temperature, the weaker is the material in terms of residual shear strength. But however, this thermal sensitivity, which is very large here, it depends very much on the type of material that we are testing. It depends on the mineralogy of the clay component, because it's something that concerns the physicochemical interaction in the microstructure. And in fact, the same scholars analyzed a large number of soils, of clay soils in particular. We see a very wide range of liquid limits and plasticity index in this classification chart. And these are the results that they obtain in terms of effect of temperature on the strength. They call positive effect an effect that is consistent in sign. High temperature, high strength; low temperature, low strength. They call negative an effect that it's reversed, that it's inconsistent with that, so meaning that strengthening upon cooling, weakening upon heating. And they noticed that the more smectite, the lower the friction angle the material had, the stronger was this cooling induced weakening. And the magnitude of this effect is very similar to the magnitude of thermal pressurization, actually, 1.5% per degree, suggesting that probably the phenomenon has the same physicochemical root. Interestingly, this pattern is only valid for slow shearing, the typical slow shearing that is done in the laboratory. If the soil is sheared fast, and fast I mean above 0.1 millimeters per minute, which in terms of landslide movement corresponds to rapid landsliding, the behavior is reversed, and smectitic clays weaken at high temperature, which is something more known in the literature for fast landslides. In fact, we in our laboratory are exploring whether on the opposite side, non-smectitic clays, for example, kaolinite, would actually strengthen at fast speed, and it seems that it is like that. The author in these publications used also a classic approach, which dates back to the studies of Tika Lemos and Peter Vaughan at the Imperial College in the 90s, to explain this temperature and shear rate dependent coupling in terms of weakening or strengthening with the prevailing mechanism of shearing, the mode of shearing, they call it, in the shear zone. And just to be complete, moving from the residual strength to creep, which can be volumetric but also shear creep and its dual, stress relaxation, we find from the literature that both of them depend on temperature. And again, we are going in our laboratory to make tests on that, doing a shear creep test in direct shear devices. And key to understand why creep depends on temperature, we need to look again at the microstructure, at the interparticle bonds and the chemical bonds, how they are broken at higher temperature with more ease. And there is consensus that at elevated temperature, creep is more likely and is faster, but relaxation is more rapid. Now, after this big overview of the literature, why I told you all this? Well, because in the field, the temperature of the slope is not the same across the world, first of all. It's not the same with depth. It's not the same over time. Temperature changes continuously in the slopes, especially in the shelf of 5 to 10 meters of underground. Temperature is continually varying. And it's also changing over time, over a long term, again, I mean decades, century, because of climate change. And for example, in this figure, there are thermal patterns which are calculated just with heat diffusion equations, very simply in GeoSlope software, that summer, autumn, winter, spring season have different patterns of temperature in the underground. In particular, you have a thermal inversion layer in winter where you have a lens of soil that is actually warmer at a depth that can be 5, 10 meters, because it is the heat wave that is propagating from the summer, and it takes several months to reach that depth before it fully dissipates and before a new wave comes because of the new spring and new summer. So the pattern, it can be even irregular, it's non-monotonic. But now think of having a slip surface, a landslide in this slope. Clearly, the slip surface is crossing layers of soils at different temperature. So even if the soil is completely homogeneous in terms of other properties, and you want to do an analysis considering a homogeneous soil, well, that soil is not homogeneous with respect to temperature. It has patterns in it. And as a result, especially if that soil contains clay, at different depths, you will have a different peak strength, different residual strength. And we can argue that the safety factor, we are doing this analysis in these days, the safety factor over the seasons and in time, because of climate change, can really change a lot, can change by 10, 20, 30%, depending on the areas of the world and the depth of the slip surface. So it's not something that should be simply neglected. It has to be calculated. That's why I advocate for a thermo-hydromechanical approach to soil slope stability. We need to include temperature in this model to increase the accuracy of this model. I can even argue, but this is now it's speculation, it's more for fun, that imagine you don't have a slip surface, but a landslide is going to happen soon, and the slip surface starts to form. If it forms in summer or in winter, maybe the slip surface will not be the same, will be more or less deep, because it will start to, a slip surface forms following weak layers, following weak material. And if the material is weaker at a certain depth, you might have, again, speculation, more deep-seated or more shallow landslide triggered in summer or in winter, just because of the different temperatures in the underground. From speculation, let's move, and I'm almost finishing, to actually a real case. This is the same case from these guys from Japan that actually found a real landslide that could be explained only because with changes in temperature. There were actually a group of landslides in active clays in a certain region in Japan, and they went to the field. They could not understand, why is this landslide moving? Well, there is no rain, no snow melting, nothing, no earthquakes, pore water pressures were not changing, yet every year the landslide would move in autumn, in late autumn, when the soil was actually cooling down. They took samples, they analyzed them in the laboratory, and they actually found out, and I showed you before, that from room temperature, while cooling down this material, the friction angle would decrease, and that is what could explain, the only thing that could explain this periodic landslide reactivation. I think it's a great case study. But beside these, and maybe a couple of more studies that suggest a similar phenomenon in the field, evidence is actually scarce. And I think we do not have evidence for two reasons. And one reason is that we are not searching for it. We are not looking for evidence because the models that we are using simply do not have temperature in it. So we will never be able to see thermal effects if our stability models, constitutive model, or even regional scale susceptibility model do not include temperature as a parameter, as a variable. You will never see it simply. And why you are not including it? Well, because traditionally hydromechanical approaches in slope stability work well enough. Of course, they have uncertainties, but so far we have accepted these uncertainties. But maybe these uncertainties are large, especially in some cases, maybe 15–20% uncertainty has become unacceptable. And we have to make a step further, use a more advanced model to actually find better answers. Same goes for regional scale analysis. We have a lot of studies using morphological, geological, hydrological, land cover variables. In some cases, susceptibility models use geotechnical variables, but very little cases, because typically geotechnical parameters over large areas are not available, or they can only be calculated based on the lithology. So it's not a new variable, it's not independent. And surprisingly, or maybe not so, over 600 landslide susceptibility studies, which were analyzed in this review paper by Paula Reichenbach in Earth Science Reviews in 2018, none of these 600 studies ever considered temperature in any way. Temperature of the soil surface, temperature in the underground, never. Even though, and that's interesting, surface temperature data are available. They are measured by satellite, so you could even readily try and input it in your susceptibility models. And we have done so, and it actually works. Before I move to that, this was one reason. The models do not include temperature. The second reason why there is not much field evidence is because the field is not as simple as the laboratory. In the laboratory, samples are homogeneous, are simple, you control the conditions. But in the field, you have different lithologies, in fact, different type of landslides, and so different thermal effects. For example, this table that comes from our paper in geomorphology shows the possible effects of temperature depending on the depth of the shear zone. So shallow versus deep-seated landslide, thermal effects are different. Thick or thin shear zones, effect is different. Planar or rotational landslides, clay or non-clay materials, initiation, triggering or run-out phase of landslide or remobilization, slow-moving versus fast landslide, normally consolidated versus over-consolidated landslide. We have analyzed all these aspects to try and understand the possibility of different thermal responses. So if you study an entire country and think of, okay, with climate change, the surface is going to be 10 degrees warmer. Are we going to have more or less landslide because of temperature? I mean, of course, because of weather, storms, you are going to have probably different patterns of landslide. But excluding that, just because the soil is warmer, the ground is warmer, are we going to have more or less landslide? Well, it's not easy to answer because of this large heterogeneity. So we have to make subsets, sub-regions which are more homogeneous, and then perhaps we can say something. For example, let's only take slow-moving landslides in clays. We are doing this for the case study of Italy. We are in progress of publishing something that shows that in Italy, slow-moving clay landslides are actually affected systematically by temperature, and we can see these patterns statistically. But another, and this is my last slide, another successful case that we have already published in scientific reports is the following one. We took the inventory of landslides in the epicentral area of the Wenchuan earthquake in China. And this area is, of course, dominated by a single trigger, the earthquake, and a single lithology. There is a single lithology which is poor in clay minerals, actually. And we analyzed the patterns of remobilization of co-seismic landslide deposits for 10 years after these strong earthquakes. We compared it with the temperature of the slopes, the surface temperature of the slope that could tell you something also of the underground temperature, of the basal temperature of these landslides. What we found, quite interesting, was a good correlation with surface temperature and between surface temperature and the abundance of landslides on certain slopes. It was found that for this material that it's non-clay or non-active clay, so it's consistent with the laboratory analysis, warmer slopes meant more landslide, more remobilizations along those slopes. Quite interesting, but of course this is a statistical work, meaning that it can give insight, but correlation does not mean causation. So this requires an in-depth study. I wish to conclude by saying that this topic, this thermal geomechanics and this thermal slope stability seems quite promising, and I'm open to collaboration, of course, to develop modeling approach, and even more importantly, to find field evidence that would support these approaches in other parts of the world. And finally, I wish to thank you all again for listening, and Roberto for inviting me and for organizing this very nice online event. Thank you very much, Roberto. I'm of course open to questions.
All right, thank you. Thank you so much for this wonderful presentation, Dr. Vito. Let me check if we have questions here. We have some acknowledgements, very smart presentation, sounds very interesting, great presentation. But I think we don't have questions, right? We have yet 4 minutes if there is someone who had any questions.
Of course, Roberto, every time I make a presentation, I forget to write my email address on the cover. So, because if someone has questions or wants to contact me, of course, they can do so by email. But I am positive that there is no one in the world with my name and surname. I haven't found yet. So if you type my name and surname in Google, it will, my profile, my socials, my academic profile, my ResearchGate will appear in the first page, so you can just click and contact me anyhow, and that will not be a problem. I will be very happy to answer questions related to research.
Yeah, let me read you those questions. Has this thermal work only been done in clays?
Well, no, not only. We are also having experiences in non-clay, in sands, and in rock, also in various types of rocks. But in clay is where I would focus my attention first, because the thermal sensitivity of clays is way larger than that of other materials. So I think it's particularly important in clays, but it's possible it's present also in other materials. In rock, rather than a shear problem, I see more a volumetric pressurization problem with temperature. That is, I think, what I feel it's prevalent in rocks.
All right, thank you.
And if I can say, this last slide about the earthquake-induced landslides in China, well, those slopes were really almost not containing clay. The co-seismic deposits were rock debris. So that actually is a correlation that we found in rock debris material. Granular, coarse, so not really clay.
All right. Thank you. Thank you so much. I think we don't have more questions. Thank you, Gianvito, and thank you again because for what you did to prepare the presentation, and it was an honor for us to share with you this time.
Thank you, Roberto, and thank you, everyone. It's been a pleasure. Bye, bye. Till next time. Bye.
Bye, bye. All right, it is 4 p.m. and 9 minutes in Ireland. In UTC time, it is it is 3 p.m., right? And we have the next presentation. 15 and 10. Let's wait. Let's take some minutes and we'll be back. All right, hello. Again, we are about to continue with the presentation of, or those presentation of the day 2 of the Landslide Scientific Assessment Conference, Landslide Hazard. We had, unfortunately, a problem. We don't know what occurred. Maybe some confusion with the times, or we don't know. The presentation of Dr. Estella Moreira. But now we are going to continue. I am very happy to be here with Minot Theresa Abraham. It is an honor for us. I can sincerely say that one of the researchers I followed, I am interested in her research works, and even greater the honor for us to have you in the Landslide Scientific Assessment Conference. Hello, Minot Theresa, how are you?
Hello, I'm good. And I'm very happy to be here. Thanks for the invite, Dr. Marin.
Thank you so much. And the title of the research paper we shared and we announced is Developing a Prototype Landslide Early Warning System for the Darjeeling Himalayas using Sigma model and real-time field monitoring. I invite all of you to download the paper. We shared the links and also the many other research papers published by Dr. Minot Theresa Abraham. So as I asked to the other speakers, we want to that you present yourself about where are you working right now, maybe your affiliations, and yeah, then you can start with your presentation. And thank you so much again.
Thank you. Is my screen visible, the full screen?
Yes.
Yeah, thank you. Yeah, so hello everyone. I'm very glad to be here. So this is Dr. Minot Theresa Abraham. I just completed my PhD from Indian Institute of Technology Indore in India. And recently, like in October, I moved to Germany to join as a Humboldt Fellow in RWTH Aachen University. So from December, my affiliation will be RWTH Aachen in Germany. So currently, I'm doing my German language course sponsored by the Humboldt Foundation. I'm really grateful for the foundation. Also, but the work currently I'm presenting is a part of a project which has been carried out by my PhD supervisor, Professor Nilima Satyam from IIT Indore, with the financial support from DST India. So the paper is authored by myself and my supervisors, Dr. Nilima Satyam and Dr. Bishwajit Pradhan from UTS Sydney. Along with us, we had our collaborators from Italy, Dr. Samuel Segoni, and from Saudi Arabia, Dr. Abdullah Alamri. So all of us have worked on this project, and this has been the project principal investigator was my supervisor, Professor Nilima Satyam, and I would sincerely like to thank her for letting me work on this project. This was a very interesting project, which I did apart from my PhD thesis. So we worked on this particular location since 2016. So this is where it is. I hope all of you know where India is. So Darjeeling Himalayas is a small part in the northeastern part of India. And like we did the study in a very small town, Kalimpong. So as you can see over here, it's the northeastern part of India, the part of Himalayas. So yeah, so this is the town. Its name is Kalimpong. It is part of the Kalimpong district in the state of West Bengal in India. So as you can see here, the town itself has a big, rich topography. So here is a ridge, and it is sloping towards both sides. So on one side, it is draining towards the river Teesta, and on other side, it is draining towards the river Reli. So here we can see that a lot of drainage paths are there. And on this side towards T star, it is very highly rugged mountains and the slope is very steep. And on the other side, we have a gentler slope. So we found like after a lot of field investigations and everything with my supervisor and an NGO was working there, Save the Hills. So they also helped us with the field investigations. So after investigations in 2016 and 17, we have found that this region, the Shibo Pasture region, as you can see over here also the photographs, this region was highly affected, and every year minor slides and major slides, landslides were happening in this particular region. So this is basically the system of Joras. That's what they call the mountain rivulets. So this is how the system of drainage works in Kalimpong from the ridge towards both the sides. And we could see failures varying from minor cracks in the roads to debris flows in this particular region. So after understanding this, we first inquired the triggering factor for landslides. So in 2011, there was Sikkim earthquake, and there were many landslides which got triggered due to earthquake. But most of the landslides happens during monsoon season, and the rainfall is identified as the major triggering factor for the occurrence of landslides in this particular region. So when we identified rainfall as the primary triggering factor, the first thing that we tried was to understand the rainfall threshold conditions, which will trigger the occurrence of landslides in the region. So we started from the basic traditional ID thresholds. But we do not know which threshold will be suitable for this particular region. So this is a very important question to be addressed. So, and what we did is like we adopted different approaches, like the ID thresholds, the ED thresholds, the probabilistic approach, and the hydrometeorological approaches. And then we compare different models to identify which is the best performing model. So that is the first approach in this case, the rainfall thresholds. Then we installed 6 sensors. You can see in the previous slide that you can see these dots over here. This is a system of sensors, which we have 6 numbers that are installed very near to 2 mountain rivulets, which will monitor the tilt rates and the volumetric moisture content of these particular locations. So this is the second phase. And then what we did is like we found that both these methods had some flaws, technical flaws when they were used individually. Then they combined both of them using an algorithm-based approach to get a better performance. So the first approach in this was, as I told you, the rainfall thresholds, and the first conventional ID thresholds. We know that ID thresholds is plotted on a logarithmic scale as in the rainfall intensity versus duration. And again, we know that this was used since after the pioneering work of Kane in 1980. But the recent works, they focus on more on the ED thresholds because intensity is again defined as a function of duration. And the interdependability of variables is not a good thing to when we explain something mathematically. So that's why we are now going towards the event versus duration thresholds. So these are the threshold equations derived for Kalimpong, ID and ED. Actually, both of these are interchangeable, easily interchangeable. And there is a relation also between these two variables because intensity is defined as the ratio of event and duration of rainfall. So we had these thresholds initially, but we found that these thresholds were issuing a lot of false alarms. They were very conservative, but the number of false alarms, if they are too high, we know that we are going for a forecasting system and people should trust on the warnings we issue. So if we issue a lot of false alerts, the reliability or the trustworthiness of the model is under question. So we should find a way to control these false alerts. So that is how we went with Sigma model. So Sigma is already in operation in Italy. So we followed the articles published by Martelloni et al. In 2012 and later. So adopting the methodology used for Italy, we customized the model for tackling Himalayas by using the data, the rainfall data from 2010 to 2015. And then we validated the model with the landslide and rainfall data with 2016 and 2017. So in Sigma, what we do is, like as the name indicates, it is related to the standard deviation of the rainfall data. So we actually compare the rainfall on the day of occurrence of landslide, or based on the forecasting. Is it actually varying from the standard deviation that we have observed so far? How much times it is varying from the data that we have observed so far? So we consider both short-term rainfall and long-term rainfall, and we assume that the data follows a cumulative distribution, which is similar to the Gaussian function. So this is how we have approached the Sigma for Kalimpong, and this is the distributional algorithm we use for Sigma. So how this works, we have two different set of vectors, which is initially based on the first 3 days, and then from 4 to 63 days. So this 63 was customized for Kalimpong. We can, like when we did the same work for South Indian districts like Idukki and Wayanad, the number there much lesser, like 30, 25, like that. So this number can also be customized based on the regional specific data. So here we have different thresholds, which is related to the standard deviation of the data. And these are also customized specifically for a region. And the algorithm is also customized for darjeeling Himalayas. So what we check first, if the vector, the short-term rainfall vector is greater than 2.5 times sigma, so we issue a red alert. If it is not, we check if it is greater than 2.05 times sigma. If it is yes, we issue an orange alert. If both conditions are not satisfied, we check if it is greater than 1.65 sigma. If yes, then yellow alert. If that is also not there, we check for the long-term rainfall condition. If it is greater than 1.95 sigma, then also we have to issue an yellow alert. If there is none of these conditions are satisfied, we have a green alert, which means that there is no warning. So if there is red alert, we expect landslides. Orange alert also we expect landslide. Yellow alert is like we have to watch the situation. That is the meaning of yellow alert. But still in the study, we have considered yellow alert also as a positive warning, because we are actually trying to minimize the warning to the best possible extent. So this is how the sigma curves are plotted initially. Then again, to control the false alarms, we have a procedure of optimizations. So this 1.5 sigma, it will be, the threshold will be raised very slowly so that the false, no alarms are missed. So what happens in that process, all the false alarm will get removed without losing any true alarms. So this has been verified using a confusion matrix that you see over here. So this confusion matrix is the normal standard confusion matrix. We call true positives when both the prediction is correct with a landslide, and we call true negative when the prediction is correct without a landslide. And when there is a landslide prediction, but there is no landslide happen, that is a false positive. And the landslide happens without an alert, it is called a false negative. So we do not want false negatives and false positive. False negative is a very critical case because we are not supposed to miss any event that is more critical, but we cannot be too conservative at the same time. So we compared all the models for the years 2016 and 17, and then we understood that sigma has a very good performance with like very high value efficiency and likelihood ratio when compared with both the ED and ID threshold. And we can see that the number of true positives has increased and the number of false positives has reduced considerably by using sigma. Yet sigma also has a number of false positive 55, which is not a good number. We still have to reduce that. So here comes our monitoring system. We have 6 sensors installed, as I have told you, in the Shibo region, which is closer to 2 rivulets. 3 sensors are installed near Carrera Jora, and 3 are installed near Osijora of Shibo region. So we have a data logger system. The 6 sensors, they will transfer the data first to the data logger, and this will be transferred to the server we are having in our laboratory. So we'll be getting the data for every 10 minutes for both tilt rate and volumetric moisture content data. So we were monitoring this slope since 2017, and we have data till 2020 was used for this particular study. This was published in October 2020. So, so we had displacements every monsoon, and we found that the displacement rates, whenever there are actual field displacements in the field, the tilt rates are also going very high. But there were some tilt rates which are not associated with the slope failure as well. These were from external disturbances, some vehicular movements, or some animal disturbances like that. So we found that tilt rates are corresponding to the control displacement, but still there are some faults alerts which are not related to slope movements. So we found that the slope movements are always associated with rainfall and tilt rates. So if you combine both these methods, you could avoid a lot of faults alerts. So the first occasion where tilt sensors 1, 2, and 3 were there near Piari and Ijora was found to be more severe, experiencing more severe slope failures than the other one. So we proceeded with the study with these 3 sensors. And what we did is, like, we first have the thresholds, ED and I thresholds. So we check if the threshold line with the 5% expense probability is crossed or not. So if this is crossed, then we check the tilting rate. If this is also crossed, exceeding a threshold limit, then we issue an alert. But if the rainfall is crossed, but there is no tilting rate, then we have an attention. And again, there are some situations where today there is no rainfall, but it was raining continuously for the past 2-3 days, and due to antecedent soil moisture conditions, the soil is still wet, and then there is a minor slide or displacements that is being seen in the soil. So to consider this aspect, we check if any rain has happened less within a lag time. So for the Kalimpong, took this lag time as 72 hours after a lot of calibrations. So this value should be calibrated particularly for every region. And if that is all crossed, then we check the tilt rate threshold. If that is crossed, again alert. And if both there is no rainfall, then there is rainfall within the lag time, then there is no warning. And there was rainfall which is exceeding the threshold limit within the lag time, but the tilt rates are not exceeded, so we have to be on an attention. So this way, we can control the faults alert issued by the rainfall thresholds, because we have the controlling factor over there, the tilt rates. And at the same time, the change in tilting which are not associated with rainfall, it is not considered for issuing an alert. So when we optimized this, we could understand that the fault alerts were controlled to a very large extent, as you can see from this graph over here, and the likelihood ratio and the efficiency of the model also got increased. So with this understanding that when we integrated it with the ID and AD thresholds, the performance got improved. So we understood that why won't we integrate this with Sigma model? So in Sigma model, the most of the fault alerts we were getting were an yellow alert. So we added this particular control parameter to the yellow alert case, that the yellow alert will be issued only if the tilting rate is also exceeded the threshold. So all the parameters that we see that we saw in the previous slides, Sigma model, were recalibrated using the data till 2018, and so you can see that the threshold values have been changed. And then we compared it with all the models, and we can see that when we recalibrated Sigma, it itself improved the performance a lot. But the Sigma plus tilt is the best performance among all the models. So this is how we have understood that Sigma plus tilt could be used in an operational landslide early warning system with a reliable number of fault alerts, and with a very limited number of fault alerts, but a very reliable number of true predictions. So from the analysis which started in 2016, and this study was published in 2020, so the continuous 4 years since 2017 July of monitoring observations. So we understood that the rainfall thresholds we have derived, we always have derived multiple thresholds for any region to understand which model will be performing better for the region. Because we did this for Kalimpong and we found that it was performing better. But when we did the study for Kerala, like for Idiki and Wayanad for the my thesis, we found that the probabilistic analysis was even performing better than sigma model. So we do not know which model will be best suited for any particular site. So we should always follow this procedure that we adopt multiple thresholds and always take the best suited model. So, but this was issuing a lot of false alarms, and then we had the monitoring system. And this was the first ever successful, one of the very first installations that we had in India. And we are still working on, and my supervisor, Professor Neelima, she has more projects. She's now working on Uttarakhand for both like seismic and rainfall induced landslides, and we are on to more projects on the field monitoring based projects. And the tilt rates were easily correlatable with observed displacements in the field. And we understood that Andean rainfall plays a very key role in the stability of slopes. But the tilt rates are often influenced by the anticipated factors, and there are higher false alarms due to this. So we combine both the methods, and these are algorithm-based methods. We use some decisional algorithms to decide to take the inputs from both the methods and to control the number of false alerts and control the number of false alerts. So when what we understood from the analysis is like when we combine both, it overcomes the limitations of both when they are used individually, and the combined approach using sigma and field monitoring gives the best performance and all the models, and this can be used as a part of LAWs in Kalimpong. So we have done only the forecasting part. So now we are in the process of converting this to the other part of LAWs, like monitoring. As we know, it's only one part of an early warning system. And so we are almost ready with the prototype forecasting model, which we are now trying to develop to an operational forecasting model for Kalimpong. So these are the acknowledgements. First of all, the support of DST should be acknowledged, and the Save the Health NGO. And I would like to thank my supervisor also for this, for letting me work on this project. This was indeed a great experience for me. Yeah, and this is the publications from this project. Yeah, thank you.
Thank you. Thank you so much for this excellent presentation. And let's wait for questions. I am giving all the attendants to write their, giving them time to write their questions. I am looking for any questions at the moment. I think we don't have questions. Let's take some seconds. All right, I think we don't have questions, and then I just can say that thank you so much. We are very honored. I am really honored, really, because I admire your research works, and it was a wonderful opportunity to hear you directly. So thank you.
Yeah, it is a great experience for me too to share my work. So if anyone has any questions, you can always reach out to me. Yeah, just like you can always search for my name, and like you can contact me in maybe in ResearchGate or by email, anywhere. Yeah, I'm open for questions always. Yeah, thank you so much.
Thank you. Thank you. May God bless you.
Yeah, thank you. Bye-bye.
All right, we are going to take some seconds. We are in some few minutes back. All right. Welcome again, everybody. It is an honor for us to continue with the Landslide Scientific Assessment Conference. Landslide Hazard, we are very happy to be here with you. We have plenty of time to hear the presentations. We are with some good time in our favor. So I am very happy to present the next speaker. Before, I want to invite all of you to write the questions, any comments you want to share. We are going to collect it and read it to the speaker. So you are free to write all your questions, and also we invite you to download the papers, and we share the links of the research papers published by the speakers. And yeah, I am here with Annie-Sophie Mierlen. Sorry, please can you tell us your name?
Yeah, you can just call me Anne-Sophie, but my last name is Mrayen. Mrayen.
Yeah. Thank you, I'm sorry. And we are very honored to be here with you, and that you are here with us. Two wonderful research papers that we shared in our website: dynamic numerical modeling of seismic landslide using the 3D distinct element method, insights from the Balta rock slide, Romania. And the other multiple geophysical investigations to characterize massive slope failure deposits, application to the Balta rock slide, Carpathian. As I asked the other speakers, please can you tell us about yourself? Maybe you can introduce with where are you right now, what do you do, and then you can continue with your presentation. And thank you so much again.
Yes, thank you so much, Roberto, also for this opportunity, for the great conference organization and so on. So my name is Anne-Sophie, and I'm an engineering geologist. I studied in Aachen in Germany. I did my PhD at the University of Liège, which is in Belgium. And actually, I want to talk about some work that I did during my PhD today. And now I'm still working at the University of Liège, but I switched groups. So now I'm more into geophysics approaches than engineering geology. But we'll see what the future might bring. So actually, I want to maybe generalize a little bit in the first part of this talk. I want to show you the approach to use geophysics and modeling techniques to study landslides. And we will talk about ancient landslides, so not landslide-prone slopes, but landslide that already happened. So in a normal approach, as you all know, we have a cause that can trigger a landslide or slope instability. We have different factors. I will today concentrate mostly on seismic events. And these factors can produce such slope failures, as we all know. But what happens if we have the contrary? So if we have the result and we don't know the cause? This is what actually was done during my master thesis, where I had the opportunity to study a landslide that is quite old, but it was only discovered in 2015, where we found a rock slope that was hardly damaged, and we could see that it was an ancient rock fall, and north of it we found a scarp that we could identify as a tectonic scarp. So the question was, how did this landslide came there? So this is what we call a back analysis, where we try to find the causes of such landslides. And this is the motivation that was behind this work, is actually what is the origin of these landslides, and if it's situated in a seismic region, are they linked to this seismicity, and what other causes do we have to take into account? So this is a sketch. It's you should not take it too seriously. It's just some observations that we made, that we can identify seismically versus climatically triggered landslides. What you should maybe keep in mind is that seismic landslides are often a result of seismic shaking that is amplified, for example, due to topographic effects at mountain crests, where the waves will be amplified due to this shape of a mountain crest. We also have site amplification that can be, for example, due to lithological contrast, and often we can find them in, for example, for rock slides, we find them really at the top of a mountain. Climatic induced landslides are, as the word says, a result of climatic causes, of rainfall events, maybe of groundwater pressure changes, of river erosion, and so on. So we try to identify whether we can see any sort of markers in the field where we can directly say, okay, this could be a landslide or not. Sorry, a seismically triggered landslide. A nice example for a seismically triggered landslide is the Daguang landslide. It was triggered during the Wenchuan earthquake in 2008 in Sichuan province in China. And it actually triggered a large volume of 750 million cubic meters. And you can see here on the right picture that the landslide scarp is quite impressive, with a net of 700-meter height. It also formed a landslide dam, so it triggered towards the valley and dammed up the river there. So if we have a look at the digital elevation model before the failure of the slope, you can see in the white hatched line, you can see the outline of the area that was affected by landsliding. And you can see here that we have a peak of 3,047 meters. And now we'll have a look at the post-failure, so after the seismic event. Now you can see that here this peak has been taken away by this landslide. And also we have a large spread of all this debris towards the valley. And you can see that here the ancient river course was blocked completely. This is why we have here this landslide dam built up. This is quite impressive, and I would like to ask you to keep this digital elevation model in mind, so to see that we have a narrow source zone and all the spreading that a seismic event can trigger in a hard rock mass. So how do we study these old landslide sites? We try to have a look inside with geophysical techniques, and there I will show you 3 techniques that we can use. Then that we collected is put into geomodels where we try to infer geological volumes and sliding horizons, shearing horizons of the landslide, and we also attempt to reconstruct slopes prior to the landsliding. And the last part would be the geomechanical modeling, where we do the back analysis to try to understand more of factors that trigger these landslides. So let's talk about these geophysics techniques. I try to make it quite easy. If you have further questions, you can always contact me or ask me these questions later. The first technique that we use is ambient noise. So ambient noise is in the ground everywhere. It's induced by wind, it can also be induced by cars, by roofs, and it's the soil vibrating. And we can measure it with velocity meters, seismometers, geophones, and so on. And we measure actually the resonance frequency, but then we also need the velocity of the ground. For example, here I can show you this sketch. We have a sediment cover and a hard rock basement. And actually between the sediment cover and hard rock basement, we have a so-called impedance contrast, if you suppose that here is a difference in density. So this sediment would have a lower density than the hard rock basement, and also the velocity would be lower. And as the impedance as the product of velocity and density, we have this kind of contrast that we can measure with our method, and this measurement result would be a resonance peak. So this peak is a function of this impedance contrast. And so this method is also used in microzonations for earthquake analysis of urban areas, for example. So this is an example, an application example that we did on a Chinese landslide. It was also triggered by the Wenchuan earthquake. And so you can see here the measurement points, and actually higher frequency peaks are linked to lower or shallower depths of impedance contrast. So we have less material there because now we have an impedance contrast of the loose material of the landslide because it's all broken up, and of the in situ, so the intact rock that is not affected by landsliding. And we can see here at the basis, we have thicker landslide deposits, and so we have lower peak and frequencies. Another method that also uses this ambient noise is by using a multiple of these seismic stations, where we infer for the S-wave velocity of the ground. And again, with this impedance contrast, we can measure horizons. So in 1D depth profile, where we have then, for example, a contrast again of landslide material over in situ bedrock. A second method would be active seismic measurements. Here we also use that we induce them actively with, for example, hammer shots, and measure these with geophones. For example, here we have this Rainfall pickings that we then infer for a seismic P-wave tomography, as you can see here. Here's an example of this application on this Belgian landslide. The upper profile is a landslide where you can see one single velocity of this area, and below there's a profile that was measured within the landslide area. And interestingly, we could find two different velocities, while the higher velocity, I mean, the upper part velocity is lower than the in situ rock. So we interpreted this velocity as landslide mass. So this landslide mass is broken and it has a lesser velocity. And so we could here really digitize the shearing horizon of this old landslide. And the third technique is electrical resistivity tomography. This is maybe the most known technique, where we induce electrical currents down in the ground and we measure apparent resistivity. And then we get the electrical resistivity of the ground. And here's an example of the profile that we measured on the landslide, and this is the sediment sediments, and we can see that low resistivity, high conductivity, with the lake. So we measure no rock slide. So this is interesting. As we applied it here on the Belgian landslide, we could even map a fold going through this landslide, going from the scarp in the same orientation, because here, we have this lower that are linked to more broken material. So there is also water infiltration, and we have higher connectivity. So now let's concentrate on the Balta landslide that I wanted to talk about to you in the Romanian Carpathian Mountains. So you have here Europe, you can see the mountain belts of the Carpathians, and their site is marked by the red star in the southeastern part of the Romanian Carpathian Mountains. And actually, not many people know that this area is a seismically active region. All these blue dots here on the map show epicenters in the years of 1900. And you can see that we have also epicenters of magnitudes above 7. And actually, during the last 300 years, there have been more than 2 earthquakes with magnitudes 7. And our study area, the Balta landslide, is exactly here in the Buzău region, so the Buzău province. And it's next to 7. We have to note that these earthquakes have a focal depth that is varying between 90 and 150 kilometers. So that is what we call intermediate depth earthquake. And this is maybe not that known because these earthquakes don't have such a superficial intensity as maybe that are in shallower depths. These earthquakes are known to cause human losses and also landslide triggered natural disasters. So now let's have a look. It's a photograph that I took from the Balta landslide, and you can see that it's quite lots of trees. And here in the back, you can see an outcrop of rock. And actually, this is our landslide scarp. And all the mass came down towards the valley of this landslide. So this is the whole area of the landslide. And if we have a zoom to the landslide scarp, we can see that here again, we have a really large scarp that I like to compare to the Daguanbao landslide. Even if it's not that impressive, it's still a really sharp scarp. And just in front of it, we have this plateau area with this really flat area. And yeah, that's quite interesting, I think. And we have here now a regional scale view of the area. And as you can see here by the outlines, the Balta landslide is not the only landslide in the region. So this is a highly active region for landsliding. We try to identify more landslide with this kind of sharp morphology. Unfortunately, we could not find any other shape that was this impressive. The other landslide make more think of flows actually, and are shallower. But still, it's a landslide prone area, and we can see here in the lower geological map that the landslide is sitting on a reverse fold, an ancient reverse fold, and it's in a Palogene geological milieu. And actually, this is made of flush rock, and flush rock is highly heterogeneous because it's made of shales and sandstone banks. Okay, so here we have some Google Maps pictures. You can see again the landslide triggered near to the crest. We have the scarp area, and then we have this flattened plateau area and the foot and the toe. And actually here you can see that this landslide gives the impression that it pushed the river kind of away. And this is also some point where we're asking whether this landslide maybe might have blocked the river or caused a landslide dam actually. And now you can see here on the lower right picture that the landslide scarp is marked by this strata. And it's dipping towards the landslides or the mountain actually, with 50 and 40 degrees. So this means that here we have what we call an anti-dip landslide, which normally is marked by higher stability than, for example, if we have vertical strata. This could be affected by toppling effects and so on, or strata dipping towards the valley is also more likely to have detachments towards the valley. But this slope is an anti-dip slope, which makes it even more impressive. So here I have a small animation of the Balta landslide with the imagery that we have. So here you can see an ortho project on the digital elevation model that is high resolution, and we got it from local researchers. And there we have our imagery with the electrical resistivity methods. Here you can maybe just remember that. So the blue would be the lower part of lower resistivities, which maybe could mean that we have higher groundwater circulation on the foot of the landslide. And here we have the seismic tomographies combined with the seismic noise measurements. What you can see here is our interpretation in terms of logs. So these black logs is just the depth profile of the HV measurements that we got. So it's the depth that we interpreted as being the sliding or the basal shearing horizon of the landslide. So by these logs, or by these measurements, we have then several estimates of the landslide thickness. And this could be digitized then to the lower basal shearing surface, and then we can calculate a volume as we also mapped in the field the extensions of the landslide mass. And actually this volume was estimated to about 30 million cubic meters, which is quite high. So if we now cut it open, we can see that we have deposits reaching 90 meters of depth in the central part. And here, what you can see is a 2D section with a green line, and this green line is an attempt to remodel the pre-failure slope. So how was the slope before this earthquake occurred? And it seems maybe this is kind of overestimated, but actually I can show you later we have a problem with the volume and the narrow source zone. So we tried to push it back against the headscarp, and it was quite a lot of volume to model. And we then got a shape with all these profiles that we interpret as our prior model. So here you can see that the green mass now was pushed against the headscarp. So the geophysical part was published last year in the Geophysical Journal International with my very nice co-authors. I wanted just to show you again, even though it was already in the animation, that we have here on the lower bottom resistivities, then here on the plateau area. And actually either it could be that here the sediments are more saturated, or that maybe here on the plateau the material is less crushed actually than in the lower part. This is also quite interesting, that we could have materials close to the headscarp because it doesn't travel as long and it has maybe was less powerfully smashed, that maybe this material is more intact and not as much resistive. So if you have now a look at our seismic data, this is what we call dispersion curves, and we could actually combine two methods. So with the seismic array and the multi-channel analysis of surface waves, what we get from the active seismic measurements, we could combine here the frequency spectrum so that we get even a more detailed 1D profile of the depths. And you can see here that we have in this part of 60 to 80 meters depth that we have a contrast. So we estimated this change in velocity. So we go from 400 meters a second to 900 meters a second. That this contrast means that above there is the landslide material of less velocity, and below there is the higher velocity rock, in situ rock that was not touched by landsliding. So this is how we can also estimate the depth of it. And we combined it with the active measurements. And actually, interestingly, we also calculated the Poisson ratio for the sediments, and we got quite high values for this. We don't know why these values are as high. So if you have any ideas, please let us know. We think that's just due to the highly saturated area, or maybe due to the clay minerals that we can find. With the HV measurements, so this is the ambient noise with the single seismometer, we took this whole point. So this is the black logs that I showed you. And for example, at the toe, we have a frequency of 2.5 hertz. At the plateau, we have 1.3. And then we could calculate with different velocities the depths. As for example, here for the plateau, we took a higher velocity because we could measure the higher velocities with our active seismic measurements than for the toe area. And so we could then infer the depths along this profile. And as I showed you before, we then had this kind of remodeling. Actually, for example, for the third profile, you can see that we have no soulstone, but we still have debris depositioned. So this was a general problem, that we have this large lateral spread of the material, so that we had to push it back to this narrow scarp zone. And this is what I wanted to compare to the Daggerwang landslide, actually, that it's quite possible, and with these kind of rock slopes, to have this large expansion of material. And so we built a central ridge and a secondary ridge to get this material back. And actually we were inspired by the topology of the area. So here is our model. And if we just project the new digital elevation model that we created on the real digital elevation model, you can see that we reflected actually here the orientation of the ridges. So what's now following is the dynamic back analysis with the numerical distinct element method that we published this year in Engineering Geology. And we then used this reconstructed slope. Our model was set up with tetrahedral elements, and we made them deformable using finite difference elements. And actually, we have here a contrast in element size, because we modeled the upper surface with less strong physical properties due to erosional and surface changes in the upper part of the soil. This is what we measured in general. The higher upper 30 meters were highly affected by, for example, ground. So we didn't want to just have the whole model with one set of properties that were made here. This difference, and also for the seismic wave transmission that we wanted to model later, we needed smaller elements here at the upper part. So you don't need to remember anything from this table. I just want to show you that it's convenient with these geophysical methods that we directly can invert for the elastic parameters that we can use directly in our numerical model. The plastic parameters were taken from literature values because we didn't have any laboratory measurements. And for the discontinuity, so for the joints, we actually got the friction angle from a joint reduction analysis. It's 49 residual values after initial slip. Here you can see the structures that we used to study the slope, because we tested different structures to see what kind of structure would be important in this case of triggering. So we have first the bedding structures of the fluid to represent the anti-dip. And then we have the joint sets that actually were measured by and also published by another work, I forgot to mention it here, of a master student of ours. And these joint sets are actually in bedding, so that if we combine both, we have this nice structure here. And we have a last one where we had to numerically install a rupture surface to simulate a rock sliding surface, and we modeled it with 15-degree inclination. So in a static analysis, this means we just want to have the slope in its actual conditions. This means we load it only with gravity, as there is no other force, no this size. And we have this strength reduction analysis done for the joints and the material. And we could see that the critical parameter is the friction angle of the joints. So we put it here, and you can see that it drastically decreased by varying the friction angle of joints. And so we decided to keep the joints above 42 degrees to have a statically stable slope. And also for the internal friction angle, we went above this 45 degrees. And you can see that cohesion, for example, of the material doesn't have this critical. So as we could prove that we have a statically stable slope and we could not bring into failure what we already kind of knew, we then tested for the dynamic effects here, because we have this seismic condition in the area. And first we used a synthetic wavelet, so a synthetic seismic signal that is called here, you can see it here on the graph, it's the Ricker wavelet or the Mexican hat wavelet, which is commonly used. And we implemented it with a ground acceleration of 1 meters per second in 2 directions. And actually what you can see here in the lower graph is that we simulated for 0.1 G at the basis signal, and amplification of the signal due to the topography and due to the material contrast gave us a 0.5 G. And these actually the most amplifying factor here is the material contrast. So having this less strong material at the surface that we modeled with lower tetrahedral mesh size actually caused a lot of amplifications in this area. And a very interesting result of this first testing with the Ricker multiplier is that the structure is quite important for the site. So if we only consider jointing and we don't consider the bedding, so we'd take the hypothesis that the bedding doesn't affect anything and it would be like one material and only the joints would affect it. We can see that here actually we only have the upper part, so the first layer that would be affected by sliding, which would cause really shallow landsliding and nothing of the traditional shape that you can actually see, and not of the deep-seated shape. So that made us understand that the combination of this bedding and this jointing effects actually causes this deep-seated rotational shape of the landslide. So we further tried to model with these combined effects of bedding and jointing, and we then used a real earthquake record from another subduction earthquake, because we think, or there is several discussions in literature actually, that these earthquakes are caused by an old subduction zone. So we use this signal to model this slope, and as you can see, we can trigger quite profoundly this slope even after 50 seconds. Lots of the material. And we could see after ground acceleration of 120 seconds that the velocity of the elements was still not zero, so it was further going down, and this is caused by residual velocity. And we have this lateral spreading of landslide mass, which is quite interesting. So the northwestern component going down to the river valley and probably blocking it, and the eastern component causing this lateral spread. Probably due to the decision of bridging this pre-failure model, which could then show that we can actually remodel the actual shape of the failure. And here we have again animation where you can see how the material is coming down the slope and is slightly starting to spread laterally and going towards the valley. So here's a final section. After 230 seconds, we could actually remodel a landslide debris at the plateau. Here we could also remodel this kind of shape, and we got 90 meters of debris, even a little bit more than we measured in reality. What we could not remodel is actually the landslide height of 300 meters. We got 200 meters, but this is actually a numerical problem, as we could not get a better spacing of the joints and the bedding because it's highly computational demanding, and so this is a computational thing. And here you have a last picture of the landslide coming down. And actually what I wanted to say to you is that it's kind of difficult to make this local analysis of landslides and to get it to a regional scale, because it's really dependent on the factors on site. So we have in general always a preconditioning of the slope, whether it's seismically triggered or climatically triggered and so on. But we also have to take into account the regional factors. So is there a seismically active region? Is there a cluster of landslides and so on? We have to look at the geomorphic factors. So seismically triggered landslide, for example, if we can see a scarp, a tectonical scarp, for example, or if we have other deep-seated shapes that we can find and so on. And we should also check for the site factors. So do we have topographical amplification potential, or do we have a geological site amplification, or do we have a sediment basin and so on? So there is lots of factors playing together to analyze the site. And also I wanted to thank all my co-authors and all the people that helped me on field, because for this kind of data you need a big group actually. And I also want to thank you for your kind attention. Thank you very much.
Thank you. Thank you so much. It is wonderful, all those research simulations, all that you are showing us. I want to read you some questions, and we invite all those who want to write their questions. It is your opportunity right now. Which geophysical technique gives the best result of landslide debris depth? What your experience say is one of the questions.
Actually, it's dependent on the site. For example, I would not generally recommend electrical resistivity because it's so dependent on clay minerals, on water content, on water saturation. It's a method that lots of people use, because it's easy to use, but I don't have the best experiences with it. I recommend for depth recognition these ambient noise measurements, so with the seismometers that you just place on the ground and you measure the noise that is naturally in the nature. But for that, you have to be aware of the seismic velocity of the ground. So this means you have to at least combine two methods. And also it's always nice to have some geotechnical information to validate, like boreholes and so on.
All right. Thank you. I don't know if there is any other question. Right
And
now,
if you have other questions, you're welcome to contact me again by mail.
all right. Thank you. Then thank you so much for
Thank you so much.
taking the time, for being here, for preparing this presentation. It was awesome. All right, we invite all of the participants to look for the research papers and all the works that Annie Sophie has published, and I'm sure I'm sure she will publish in the future. All right. We will continue in some seconds. All right, we are back. Thank you so much for being with us in the Landslide Scientific Assessment Conference. Landslide has had this day 2. We have had also wonderful research papers presented, well-known researchers and top researchers, and it is the case of Yuri Gorokhovich. Sorry if I didn't pronounce your name correctly.
No, it's good.
we have the honor of listening by the same author. Let me read you the title of this research paper published in the journal Geomorphology, Implications of Slope Aspect for Landslide Risk Assessment, a case study of Hurricane Maria in Puerto Rico in 2017. So Yuri, how are you? How is it going?
Good. Good. Thank you. Thank you very much. So can I start now? Can I
yeah,
start?
I want to ask you that you present yourself. We want to know about your affiliation, and you can go ahead.
Okay.
Thank you so much.
Thank you. Thank you very much. So it's also a great honor to be at your conference and make presentation. I value everybody's time, so that's very nice of you. And my name is Yuri Grokovich. So I work at Lehman College, which is part of City University of New York, and a department called Earth Environmental Geospatial Sciences. And I'm a physical geologist, so my specialty is not just landslides, it's also coastal erosion. I use extensively geographic information systems, but lately I was busy with landslides since 2017. We did several studies. I'm going to show you a couple and make like a summary. So where we are going with this. And the paper which we wrote, Implication of Slope Aspect, a case study of Hurricane Maria in Puerto Rico, is kind of like latest of my exploration about landslide characteristics and specifically slope aspect. So that work is my latest one, and we plan to do more. We're looking for collaborators. We're looking for people who are interested in this. And, I'm going to make another presentation more updated in American Geophysical Union in Chicago. Maybe you guys will be there. So I will be happy to see you there. Maybe we'll have a beer at the conference. It's going to be in December in Chicago. Okay, so let's move on with my study. So where it's all started. So here is a map. As you can see, it's Guatemala. About 5 years ago, we wrote a paper with my colleague Elia Machado and Jeroen Melgar and Marta Gahrimani, and it's called Improving Landslide Hazard Risk Mapping in Guatemala using Terrain Aspect. So that's work was done in several areas. We went specifically Lake Atitlan, Tsohoma study, and the study was sponsored by Inter-American Institute for Global Change Research. So the point was to assess impact of landslides on indigenous communities. And my part was just assessment of landslide, GIS mapping, and basically providing some clarification what kind of landslide we're dealing with, how does it relate to hurricanes, and so on. So just from the beginning, I want to say that the work which I am presenting is relevant probably for now to the area of Caribbean Basin, Central America, where we have a lot of hurricanes. So this is a caveat, because maybe in other areas, slope aspect is not going to be such an important factor as in this area. So the three areas, as you can see, the big one is a study area by USGS, United States Geological Survey, and elevations are pretty high in Guatemala, up to 2,500 meters. That's work which we did there. And when we arrived, they provided us with data. And so here is a data set. And I just wonder if you can see a pattern here. I don't know how many of you watching this right now, but I always ask my students, I say to them, so can you take a look at this and see the pattern? And of course, I don't tell them what's going on. So probably like 80% out of 100 say that, yes, there is a pattern. If this is a river and this is a river, then distribution of landslides is very strange, right? It's sort of, right there. But there is no landslide on this side of the river. So again, this is a river valley, which is going in that direction. And you can see north is here, south is here. So this is a southeastern slope, what you see here. And the same thing you see here, it's a river, and majority of landslides occurring on southeastern slope. If you look anywhere on this picture, this is a river also. You can see that distribution of landslide is primarily on southeastern slopes. And so this is how I came up to landslides. Last time I dealt with landslides in Ukraine. I'm from Odessa, and I used to work in Odessa University. We did a lot of work on landslides. But when I came to United States, I didn't have much chance to work on landslides. So when I saw this, I was like, wait a second, this is something interesting. Why landslides occur only on southeastern side? And we're talking about Hurricane Stan. It's a remnant of Hurricane Stan. So everywhere here, you see southeastern slopes affected much more. And that's how the work started. That's how I was curious. Observation and hypothesis we had was there should be some kind of pattern, probably meteorological, climatological pattern that produces landslides on one side, because rocks here are pretty much the same. It's a weathered core of weathering, basically. It's a hugely, washed out material. So it's pretty much the same everywhere. But on some slopes, you get just more landslides, right? So there should be some other factors in geology. And so what we did analysis. We took GIS, we created elevation model, slope, aspect, and then we produced this diagram. So what you can see in the diagram is that the histogram of distribution of aspect is primarily 7, 8, right? Which is this number of degree, which is eastern, southeastern slopes. Okay, so this is the category, which is mapped here. And here is the degree interval. So majority of landslides in Sohoma is occurring on southeastern slopes and eastern slopes. So then we took the data, collected data from images. Basically, we were digitizing landslides, and we looked at aspect distribution at Lake Atitlan. And we got the same picture. So Lake Atitlan shows that majority of landslides, again, here is the peak of histogram, are located on eastern, southeastern slopes. And the same technique we used the same digital elevation model, the same slope aspect data, and we overlaid them and digitized landslides, created big database, and we got the same results. So then there is a paper by USGS. Now this is Hurricane Mitch, and that's a different hurricane than Stan, but they published extensive database. When we took it, we also realized that there are majority of landslides happening on eastern, southeastern slopes. And so that's actually triggered our interest in the subject, and we published a paper where we postulated that, basically the aspect, something that is overlooked. And when we were in Guatemala, we saw many manuals and books which people use in Guatemalan geological survey, and everywhere they had tables and variables, but aspect was not one of them, which was very peculiar because apparently aspect plays a huge role. So we started looking for the evidence. What can happen? Why do we have this phenomenon? How can we explain it? And this is the result of our statistical analysis. So again, this is the number of landslide used in analysis. Sohoma, Stan 692, 11,000 landslides used in Lake Atitlan, 9,000 in USGS, Mitch. And mean aspect everywhere was very close. It's southeastern slope, 144, 157, 168. Here is the standard deviation, and this is the range, plus minus 1 standard deviation. So the data which we analyzed at that time, we just published this year. So if you want to take this data and work with data yourself, you can go to this website. It's Data in Brief. It's one of the new publications which allows people to download data, and anybody can use them and, you know, repeat your analysis and so on. So you're welcome to use our data and repeat analysis and let me know if we got something wrong. So one of the things which we found was related to the rainfall. And this is a paper, there is not much written about Guatemala, but paper from 1965, published findings from Portig, which is a meteorologist working for USGS. And what he wrote, that upper air averages indicate easterly to east-south easterly winds at levels from 900 millibars to 400. So 900 millibars, it's about elevation of that mountain range, which where we worked, Homa, Atitlan. That's pretty much correspond to 2,300 meters elevation. And that was actually indication that something is going on. So we looked at this paper and we realized that rain season means what? It means hurricanes. It means some kind of circulation. It's a, huge circulation that occurs at this time, and a majority of it falls in the mountains, right? So we immediately made a connection to hurricanes, and we tried to figure out, okay, so maybe it has something to do with the direction of hurricane, propagation, and rotation of the hurricane. And so here is a map which we produced from NASA data, the arrows showing direction of the wind, and this is from NASA data on the wind distribution. And this is during Hurricane Stan, 2005. So this is a propagation of hurricane. And as you see, when hurricane was propagating, there are two circulation modes here. One is from Pacific, which is working in that direction. So as you can see, the wind here coming from southeast. And then there is also another couple cells, one in the north, which is in a counter-clockwise direction also, but it's a little bit higher. So Guatemala kind of like in between, cyclonic directions. But generally, our area of study located on the south of Guatemala, we didn't do much in this area. So this is where mountains are. And in the area of study, as you can see, direction of the wind is southeast. It's moving towards south, from southeastern direction, right, toward northwest. So that was pretty much interesting to see that. And we thought that might explain why do we have this issue with distribution of landslide on only one side of the valley. And then the physical explanation of that is called mountain shadow. This is the fact when you have so-called wind-driven rainfall. So wind-driven rainfall was put together by Blaken in 2006. And this explains when winds with rain. So this is like, hurricane can be the same thing, right? So when they come to the mountain, they drop in a lot of rain. Other side is dry. This one is wet. So a lot of wet material comes here. So this increase moisture in the soil. And again, we're talking about, Central America, Caribbean, it's all weathered regolith, basically. It's very loose soil material. So when that stuff get wet and with increased moisture, it's very prone to landslide. So of course, this side of the mountain would experience a lot of landslide, and much drier one is not. So we thought that's pretty good. That's very nice, phenomenon. It's very clear. It's accepted by majority of scientific community. And when Hurricane Maria occurred, we immediately looked into data. Data were published not immediately, but after a couple of years. I think in 19 or 20, it took them a couple of years to digitize landslides. And so then we found about the database, we downloaded it, and then we decided, let's take a look at Hurricane Maria and see if we got the same issue. So Hurricane Maria, this is a propagation. So here is a 1920. Those are days, and we made a mistake. We put it's October, actually it's September. So we found this mistake only when paper was going to publication. So editors told us they can't do anything else. So we decided, okay, let's leave it like this. But all the data are from September. So data source is correct. And as you can see that propagation over Puerto Rico, here is a Puerto Rico island, right? So on 20th, that was a massive landfall of the hurricane. And so the study goal was to examine the role of the slope aspect and the distribution of Hurricane Maria triggered landslide using elevation data. We also used LiDAR data, so because it was available, and we decided to see which one is better, LiDAR or SRTM. So you can look at paper for details, but generally in numerous landslide studies, the slope aspect is mentioned as one of the important factors. However, it is not included in the methodology. It's very rare you find that aspect is one of the important factors. People use slope, people use a variety of other things, soil moisture, but not actually aspect in many models. And so that was one of the main issues, I think, which we deal with. We're trying to bring aspect of the slope back to game. So here is our sort of hypothetical idea that hurricane is moving and hurricane propagating. So here is a position at time 1. This is a position at time 2. So they look like huge, like a not chainsaw, but circular saw, discs. And then this is a Puerto Rico, it's a point 1. So as you can see, when a hurricane makes landfall, most likely you're going to get northeast, impact. So like coming mainly from the northern direction. But when hurricane passes away, you get more of that stuff from the southeast. And so this is interesting, idea that when hurricane propagates, it makes impact on the terrain from different, points of view, right? So here's more information. Here is the Puerto Rico. This is October 20 in the morning. So as you can see, a lot of impact on the island actually happens from the north. And then 12 o'clock in the afternoon, hurricane shifting over the island. And so you can get more impact sometimes, from eastern part. You can still get northern impact from north and mainly like from east and southeast. And this one is October 20. It's a 6 p.m., which is, the nighttime, 6 p.m. And hurricane already moving over Puerto Rico, and you get a lot of impact from the south, right? And so then hurricane disappears, and you see the arrows here become smaller, so wind speed decreasing. Like at the beginning, you see the size of the arrows. This is a wind speed from NASA data on wind propagation, so it all mapped from NASA. And so that's what we found. And then we did similar analysis. We took data, we overlaid with the aspect. We use SRTM data and LiDAR. So on the left side, it's all SRTM. On the right side is the LiDAR. And as you can see, this is a number of landslides in relation to aspect, and that's from SRTM data. So you see a lot of northeast, and also you see southwest, right? And a little bit of western northwest. So you see kind of like two main directions, where things are coming. And the same with the LiDAR. So more or less, they tell the same story. So conclusion is that after Hurricane Maria impact, we see a close association with northern direction, followed by association with western and southwestern directions. And so we attribute this to Maria rotation and movement across the island. And it causes strong wind-driven rainfall impact, and so on. So there is also conclusion about vegetation. So, but you can read it in the paper, and I think basically this is it. So the idea now here with the study is that we're trying to see if we can do real-time prediction of landslides, because most of the time people use a collection of data over 100 years and see where landslides are. They create maps of density or frequency ratio and so on. So, but it's all based on very, like a sort of cumulative, data set without really addressing any physical force that produces landslides. So the only thing we have in real time is a movement of the hurricane. So if you know how a hurricane moves and you can trace it and you can follow its path, then you can probably, most likely, try to predict landslides. And then you can make sure that people are warned. You can bring it into preparedness, preparation, and so on. And we can even model this kind of things because hurricanes come from different angles. They have different strengths. So if we can link that physical behavior of the hurricane with what's going on the ground in terms of terrain and aspect of slope primarily, I'm sure we can try to predict, which nobody predicted landslides yet. So this is kind of challenging task. And maybe it's too much, but I don't know. But that's what we're trying to do. And if anybody is interested, we can work together. Maybe you have some ideas. And like I said, I'm going to put it more together for American Geophysical Union conference in December in Chicago. So maybe we have a time to discuss over beer or something. Okay. So this is it. If you have any questions, let me know. You can also send me email. My email, I think, is available. And I will be happy to share with you any information I have. Thank you very much.
Thank you. Thank you so much. Thank you for sharing your expertise. All what you shared with us today was amazing. Let me check if we have questions. I think we don't have questions yet.
That's okay. People might email something, or it's not easy to comprehend all information and think what kind of question I might have. So that's that's okay.
I can read here. What an interesting research. Thank you for the talk.
You're welcome.
All right. Thank you so much. Then we are very happy. Well, let me read this question. What elevation aspect plays important role for occurring landslide during hurricane?
Say it again, please.
What elevation aspect plays important role for occurring landslide during hurricane?
Okay, you mean in our study, in Guatemala for Stan and for Mitch, it was southeastern and eastern direction. In case of Puerto Rico, because it was a different path of hurricane in relation to the configuration of the island, so we got northern and northwestern directions. And you can see in the paper the histogram. So histogram is there.
All right, thank you.
You're welcome.
Well, we are very happy to continue with this wonderful event. LandScient and all of the organizers of the event. We are very grateful with all the research authors and speakers that shared with us the knowledge. And it is 17:52 in Ireland, and time in UTC is 4:52 p.m. Then we have today the opportunity to talk with other people who are interested in the landslides and all the topics that are treated here. We told you that we were going to have this discussion section. You can think about the discussion section as a room in which we can talk very relaxed. We don't have to to share specific advanced knowledge about landslides, but we can give our opinions. We can talk about we are going to propose some initial topic that can be treated in the discussion section, but as I mentioned, it is not going to be as a presentation or nothing like that. All you can find the links in the website. We are going to share with you the links of the rooms. All of the participants can connect with us, and we are going to share right now, and also you can find them in the conference website. In the conference website, you can find the links of in this case, we are going to use Meet to talk each other. There is a section for people that speak only Spanish. Hay una sección para las personas que hablan español o así no hablen únicamente español, pero desean compartir y charlar con otras personas que hablen en español, pueden ingresar. Entonces el link también lo especificamos. Tenemos 2 salas. And we are going to talk about what is the purpose of landslide hazard maps. For example, for regions, researchers, authorities. This is what I decided, or we decided to talk this time. So I am going to give me please just 1 second. Also in the chats, you can have what I just said here. Let me go to YouTube first. So please, if you want, you can go to, oh, we have a problem because it was a message with more characters than it allows. Give me 1 second. Please go also to the website of the conference website. You can go into the room, we can talk, we are going to talk. It is not going to be in this streaming. In this streaming, we are not going to share or to show what we are going to talk in those rooms. So please go to those links. I am sharing one right now. Let me see if it is okay with this shorter message for YouTube. Not yet. Here, this is the room where we are waiting for all who want to talk with us. It is going to be private, it is not going to be in the streaming. And also para aquellos que hablan español y que la discusión será únicamente en español, está este segundo link que aparece aquí. Allá les esperamos. Este mensaje fue un poco más largo también, entonces no me lo dejo enviar. Listo. Then we are waiting for you in those rooms. Also, if you only want to take a break, we are coming back in the streaming at the appointed time for the next conference. So we can see you soon. All right, we are here again. We are happy that we had the opportunity to talk with some of the people that decided to enter to the rooms. And we are also happy to continue with the next presentation. We have a great speaker and author again. I want to invite you to read the research papers that he has published, a review of recent studies on landslide hazard in Latin America, and the other paper, Multi-temporal landslide inventory analysis of an intertropical mountain in West Central Mexico, basis for hazard management. We have the links of the papers in the website of the conference. So Alejandro, thank you so much for being here. Alejandro Cesar Valdez Carrera, how are you?
Fine, thank you. Thank you.
We are going to ask you to tell us about your affiliation, what are you doing now in research, and then you can start your presentation, and thank you again.
Sure, thank you. Well, as Roberto said, I'm Alejandro Cesar Valdez Carrera. I'm working in Environmental Geography Research Center, that is a center of UNAM, is National Autonomous University of Mexico. And as a part of my PhD, I published those articles. So I'm going to share my results, my methodologies, etc., with you. Thank you to be here.
Thank you. Go ahead.
As a framework, as we know, in recent decades, the effects of that kind of processes, natural processes, natural hazards has increased. Specific, the number of disasters and economic losses. If we see America, we can see that those effects has increased and are the highest number of disasters. They have the highest number of disasters. In a specific, landslide, mass movement are related with floods and storms. So for this is important, the study of these processes and these natural hazards. So I'm going to start with the first article. My first article, and this is a review of recent studies of landslide hazard in Latin America. I want to share with you this photo. That photo was taken in my study area. It's a complex landslide I have been worked with during the last 4 years. This article was published in Physical Geography Journal. It's available for you, and was published in September 2021. As an introduction, the disasters has increased during the last 3 decades. So we can see that the effects in economic losses, and in specific, the effect of these processes has been concentrated, or has concentrated in mainly in Asia, America, Europe, and Africa, and mostly due to extreme climatic events. Hazard is expressed as a probability of occurrence between a reference period and its function of spatial probability and temporal probability. Temporal probability refers to triggering factors, and spatial probability, static, environmental, or conditioning factors. The natural hazard are associated with geological, geomorphic, and hydrometeorological processes and their combinations. And that kinds of processes, landslide processes, are common in mountain zones. And then to understand what landslide is defined as a downsloping movement of mass of rock, debris, or earth under the influence of gravity. Those processes could be suddenly or slowly, but suddenly landslides commonly have disastrous effects. And these processes are triggered mainly by precipitation, but also by earthquakes, rapid snow melting, volcanic activity, floods, and variety of human activities. That information has been referred or stated by some others in review publications, recent review publication, and that reviews focus its research on susceptibility, hazard, and risk to landslides. Then those reviews focus mainly on Europe and North America and indicate the need for studies on landslide hazard in Latin America, Africa, Southern Asia, and Oceania, especially in the intertropical regions. This is crucial because the intertropical zones are the most densely inhabited areas and could happen disasters. Well, there is a lack of systematic analysis of the different approaches of landslide hazard studies in Latin America, and for this reason, we made this research, this review, considering available literature on landslide hazards, considering the spatial distribution and temporally probability. That means that we consider environmental factors, triggering factors, and landslide inventories. About the materials and methods that we follow, the methodology consists in 3 stages. The first was the search for scientific articles. We consider Scopus, Web of Science, Cielo, Reddit, and Redalic as our databases, and the period of time that we analyze this come from 2000 and 2019. We consider all the countries that are into Latin American region, and this is Argentina, Bolivia, Brazil, Chile, Colombia, Costa Rica, Cuba, Ecuador, El Salvador, Guatemala, Haiti, Honduras, Mexico, Nicaragua, Panama, Paraguay, Peru, the Dominican Republic, Uruguay, and Venezuela. The search was made in English, Spanish, and Portuguese. And the search was made considering 27 keywords that are here in this figure, and refers all the ways to express landslide and types, and its types. And the second stage was the depuration of the articles database, and the third was the data systemization and analysis. The analysis was made considering 4 categories, and those categories were general information, study area, research objectives, and methodology. And we also consider these variables. what we have as a result. That is, we analyzed finally we analyzed 283 articles. The most predominant articles come from Scopus and Web of Science. That means that they were written as in English. And about the keywords, the main keywords that match in this analysis was landslide. That means that the most common way to refer any landslide type is landslide in this region. Almost the 70% of articles, 200, match with one keyword. Okay, about the number of published articles, almost the 55%, 54%, it's concentrated in the last 6 years, and the average from 2000 and 2013 was 7 on average. Lead authors, about the lead authors affiliation, the main affiliation was UNAM from Mexico, YANGLA from Argentina, Universidad de Chile from Chile, CONICET, Universidad de Buenos Aires in Argentina, and Universidad Nacional de Colombia. About the spatial distribution of the published research, we have that almost the 80% of the published was made, but is concentrated in 6 countries. Those are Mexico, Brazil, Argentina, Colombia, Costa Rica, and Chile. And the major production is concentrated in Mexico, following by Brazil, Argentina, Colombia. Latin America have 20 countries and only 15 countries publish about this topic. What we have about the approaches followed in this research, the main subjects covered in the publication were susceptibility, following by characterization, inventory, hazardousness or hazardness, triggering factors, and conditioning factors. The types of landslide studied was mainly referred as landslides, followed by slides, floods, and avalanches. The other researchers refer that those processes as a mix of those. The analyzed articles focus on 7 specific topics, but almost the 80% were modeling, geological, and geomorphological analysis. The remaining were inventories, hydrometeorological analysis, seismic analysis, modeling comparison, and land cover analysis. About the methodologies used in this researches were the most frequent were characterizations, followed by statistical approaches, deterministic approaches, inventory approaches, and heuristic approaches. The spatial analysis tools that were most used were GIS, for example, ArcGIS, which SciGIS, and Idrisi. They use also topographic profiles to represent the study areas, GPS, UAV, and almost the 80% of the publication use 5 words to inventory and to prove their results. The researchers also dating their processes using radioactive radiogenic carbon, uranium, chlorine, interferometry, dendrochronology, and the mainly technique to prove and to prove their results were curva rock. The analysis research use thematic maps, satellite images, and precipitations databases as the main inputs. The characterization studies has made a limited use of HydroSig, Java, TerraHydro, and other techniques and programs. Statistical approaches use MATLAB and concentrate their analysis in analytical hierarchy processes. Deterministic approach was made by Shellstar, SynMap, and Landslide. Heuristic approach use Mora Parson and Von-Westner techniques. As a conclusion, we saw a growing interest in that topic in universities and a growing interest of research in this topic, and we found that the last 6 years were the more productive, and the investigations were published by 15 countries, and it's important to report our results as not only as technical reports or gray literature. It could be better to publish this as at international journals in order to the information could be available for us. There are a reduced number of research in specific topics as hazardness, inventory, and trigger and conditioning factors. For this reason, we made firstly characterization. Is important to strengthen our groups of research groups, and there is an opportunity to use data techniques as dendrochronology, data, and this investigation represents the first review of Latin America, and that could be a good information to study of hazard from landslide in intertropical zones. The second result and the second article is the multi-temporal landslide inventory analysis on intertropical mountain in West Central Mexico, basis for hazard management. Was published on Journal of Mountain Science in June of this year, and it's also available for you. As an introduction, we know that landslides are frequent slow processes that occur in that kind of mountains, intertropical mountains. We also know about the conditioning and triggering factors because I already mentioned. Knowing the spatial distribution of that processes is important for risk assessment and management, and this is represented on landslide inventory maps in Mexico. Zones, intertropical zones, are affected by intense precipitations, and some others refers and state that it's important to do that kind of research and jobs works about the spatial-temporal prevention and mitigation in order to reduce the disasters effects. The state of Michoacan is represent an intertropical mountain zone in Mexico, and is also affected by tropical cyclones. There is a stratovolcano that is located there, that is called the Pico de Tancítaro, and we took that place as our study area. What we made, at first we made a landslide condition. We describe and analyze the landslide conditioning factors, and the second stage was multi-temporal landslide inventory. The conditioning factors were worked at detailed scale, as you can see in this slide, and where geological, geographic, geomorphological characteristics, slope aspect, vegetation cover, and land use, and follow the method for evaluation of susceptibility, hazard, and risk due to landslides of these others. About the multi-temporal, was a construction made from filework and visual analysis of satellite images and aerial photograph from 1995 to 2020, and were described using the classification of landslide of crude environments, and after that we describe the type, material, data, and speed of occurrence. This is the inputs that we use. They are mainly maps. They were mainly maps, articles, and satellite images, and also orthophotos. And for the conditioning factors were geology, geomorphology, geology, land cover, and land use. And those are the inputs for multi-temporal inventory. We classify the landslide processes and considering their type, flow and slide, material, and velocity. And this is the study area. It's located in the central west of Mexico and into the Michoacan state. It's also part of the Trans-Mexican Volcanic Belt and Michoacan Guanajuato volcanic file. That means that we have monogenetic volcanoes and polygenetic volcano. The Pico de Tancítaro stratovolcano is a polygenetic volcano, and a Paricutin volcano, that is the most famous continental volcano that we see here in Mexico. It's a monogenetic volcano. Around the Pico de Tancítaro stratovolcano we have urban localities, and the most representative is Periban. About conditioning factors in the geology, is represented by a chronostratigraphic map, and that is a compilated map. And the most representative here is that we have the Paricutin and Astillero and Pedregal activity. That is their activity is the most recent into the area, and the at least the three periods of activity of the Pico de Tancítaro stratovolcano that are represented by pink. We can see also the collapse zone and the avalanches, the two avalanches. And this is the description, the more specific description of any of that unit. And the main composition is andesitic and andesitic basaltic rocks, quaternary rocks. And for geomorphology, we have mainly mountains. Mountains are divided by summits, valleys, and slopes, followed by high hills and low hills, piedmonts, plains, and valleys. Fluvial valleys, and the most representative here are the high hills and low hills. And about slope, the most predominant slope were very steps that are located in the Pico de Transitero, stratovolcano, that is in the center of the map, and the main aspect were north and south. About the soils, we have andosols, mainly andosols, and in the top of the mountains, we have leptosols. About land cover and land use, the most representative land use that is in yellow, it's avocado agriculture. And about the land cover, we have mixed forest and oilmen field forest. Finally, what we found about the multi-temporal landslide inventory, we found 505 landslides in general, divided in slides and flus. Those were classified as extremely rapid and rapid processes. We also found we also describe their extension and the number of events per year or per period, and we also observe recurrence processes. As you can see in the image, we have the flow, a debris flow. This flow in green, and more recent, we have a debris flow. So this is the recurrence that we observe in this area. We made an analysis, a comparison, and an analysis between the polygons, the landslide polygons, with the conditioning factors, and we found that the landslides were developed on flanks of Pico de Transitero, mountain fluvial valleys, and volcanic cones, and they are mainly oriented to southwest to northeast and southeast to northwest, and they are associated with the local fracture system, were developed on steep slopes oriented to south, north, and east, on andesitic and basaltic andesitic rocks, andosol and leptosols, and mixed and oilmen forest. This is a map. I took some picture from firework. And about the triggering factors, we have we made a earthquakes analysis, and there is no antecedent. There are no antecedent earthquakes in this area before and during the processes, and the earthquakes that has been registered in this area are considered as micro earthquakes or micro seasons. Its magnitude is lower than 4.5. And the main trigger factor were torrential rainfalls caused by hurricanes and tropical storms, and they are almost they represent the 11 to 16.5 of the annual rainfall in this area. As a conclusion, we documented that it's possible to study the distribution, topology, velocity, and composition of from the geographic perspective, and we observed that that kind of studies are few and lack in these areas. We also identify the higher relative, the classes with the higher relative importance for future assessment, as for example, susceptibility and hazardness assessment. And all this information could support land use planning and disaster risk management in intertropical mountainous areas. Thanks for your attention.
Thank you. Thank you so much for this great presentation and for being with us. It is great to have a great speaker here with your presentation. So I am giving the time to all those who maybe are going to write some questions. Let me read this one. Have you identified extremely rapid to rapid velocity of landslide?
Yes, I didn't put the numbers of this classification, but extremely rapid. Well, the velocity classification was taken from the Cruden and Barnes classification, according with this. And the extremely rapid is 5 meters per second, and very rapid is 3 meters per minute. Rapid 1.8 meters per hour. And we made file work, and we identify those processes were rapid, and we try to differentiate them as according with this classification. That was the way we couldn't. It's just an approximated data. It's not a real data, but if you find for information about velocity, the flux and slide in this area always has been rapid processes.
Right. Thank you, Dr. Alejandro again. Yeah, we don't have more questions. I hope everything goes well with you, your research. Maybe we can see each other in another event in the future. May God bless you.
Thank you. See you.
All right. I just checked the conference schedule and it is 19:25 in Ireland, 7:25 p.m. Here in Ireland. Time in UTC is 18:25. So at 6:50 p.m. we are going to have the next presentation, as you can see in the conference schedule. So right now we are going to have this break. So we see you in 25 minutes with the presentation of Dr. Gabriele Gorreta Pauli. So see you then.
Hello, everybody. My name is Álvaro Matos. I am a member of the organizing committee this conference. The next presentation is entitled Assessing Landslide Volume Using Two Generic Models, Application to Landslide in Whatcom County, Washington, USA. The author is the Dr. Gabriel Legorreta Paulin. Gabriel, welcome.
Thank you. So, my name is Gabriel Legorreta Paulin. I'm working for the Institute of Geography at the National Autonomous University of Mexico. My main job here is to elaborate landslide inventory map and modeling landslide susceptibility map. So today I'm going to present a project that is in collaboration with the Washington State Department of Natural Resources, DNR, for modeling landslide volumes. We use a study area in Whatcom County, Washington, United States. So the main goal of this project was to implement two generic landslide volume models that I call the overlay and the interpolation models to estimate sediment production for large landslide inventory maps. Let me give you first a brief overview to put in context these two models and the scope of our work. In general, several GIS applications have been used to map and modeling landslide volumes, heuristically, statistically, or deterministically by using different spatial scales and with multiple scopes. Each one has its own advantages and limitations. But in general, all these approaches and methods can be classified into groups since landslide volume can be considered in two different ways. In the first group, the basal slip plane is used to obtain the total landslide volume. In the second group, the accumulated material or mobilized material is used to obtain the superficial volume. And here also there are several methods, but we use the easy ones. The one is called the overlay and the interpolation methods. The overlay method uses a real pre and post sliding topography to obtain the superficial volume. And if the user don't have a pre-sliding topography, then he can use the interpolation method to obtain the previous topography to the slides. And then he can, by using a real post-sliding topography, he can obtain the distribution of volume over long time periods. In either case, by using the overlay or the interpolation methods, these two methods are prone to some errors that can be attributed to the pixel size, to the shifting between pre and post digital elevation models, or to the interpolation method. Most of the literature showed that the errors go from -10 to 28%, but in the worst case scenarios, especially when you have a shifting between pre and post surface, or when the user uses a third, fourth, or fifth order surface to obtain the slip plane, then the error can go above 700%. Also, the potential error on calculating the volume introduced by the difference between a real pre-sliding surface and an interpolated pre-sliding surface has been poorly studied. On the left side, we have the representation of a real topography. In black line is cross-section. In the middle, we have the theoretical surface with an interpolated surface. So as you can see in orange, the theoretical surface go above and below of my real topography. That will introduce that the model tend to over or under predict volumes. How much error we can get is part of my results. So in order to address the above problems, we implement the overlay and the interpolation method in our map by using Python. We put it as a tools in our map. And then we tested the two models in a real and theoretical conditions in Soma Mountains at Watson County in Washington State. In this area, we have 19 deep-seated landslides, but we use only 8 that were mapped with moderate and high confidence. The two models can be used for shallow landslides, or can be used for deep-seated landslides, or can be used only for a single landslide polygon, or for the entire landslide inventory map. So the result of this project is split in 3 sections. In the first section, we estimate the landslide volume by using the overlay method and by using the 2017 and 2006 LiDAR image. In the second section, we address the potential landslide distribution over long time periods by using the 2006 LiDAR and an interpolated digital elevation model. And in the third section, we address the potential volume changes introduced by altimetric variations. To do that, we use the previous interpolate surface and the volume obtained with the 2006 LiDAR as a reference to be compared with other altimetric digital elevation models that have variation between 0 and about 2.5 meters. These other surfaces were created by a filtering process. So let's look at the first results for the overlay methods. The results show that the overlay method is able not only to calculate the volume correctly, but allow to the user to highlight the dynamic of the landslide volume. That will be helpful for classification purpose. So let's see this with the resulting maps and the tables. So on the left side, we have the 2006 and 2017 LiDAR image that are the input for the model. The model will subtract these two images to obtain an altimetric changes. And then it will multiply by the pixel size to obtain the volume map. In here, in the scale, you will have positive values. Positive values will represent the loss of material, and negative values will represent accumulation of material. For most of the landslide, the accumulation of material is at the top, and the loss of material is in the central part of my deposit. Now, let's look at the table that is produced by the model. On the left side, we have the landslide geometry for my 8 deep-seated landslide, and they came in a wide range of length, width, and depth. Then the model will produce 12 columns with the information of area and the volume for the headscarp and deposit, and individually for the headscarp and deposit. Also, they will produce the positive and negative values for each part of this. But let's focus on the total volume for headscarp and deposits in the column that is called volume HD. So in this column, we can observe that 6 out of my 8 deep-seated landslide have positive values. That means that during this 11 period of study, they have been active. But 2 of them, landslide 83.25 and landslide 92.29. These 2 landslides have negative values, and for that, these 2 landslides can be considered as not active or in the future as relic landslide, especially landslide 92.29, because these have negative values, accumulation in the headscarp and accumulation in the deposit. In the case of landslide 83.25, they have accumulation in the headscarp, but the deposit is still active. Another result of using the overlay method is that the user can obtain the total annual load discharged from landslide. So let's see an example of this by using the landslide 8314. This is a landslide that is called Sweet Creek landslide. It's the largest landslide in my area. It has 1.2 square kilometers, and it has a volume about 448,000 cubic meters. If we divide this sum up of volume between my time period of study, 11 years, Sweet Creek landslide is able to produce 4.1 times 10 to the 4 cubic meters per year. And if we know the soil density of this area, it will produce 9.2 times 10 to the 4 tons per year. How accurate is this value? I will say it's pretty accurate and is in the same order of magnitude as the one that was calculated in 2000 by Whatcom County Public Works. Now let's look at the results for the second model, the interpolation method. The interpolation method will allow to the user to fill out the amphitheater shape depression of landslide, and that make a simplification of the landform. With that, we can compare with the LiDAR 2006 and obtain the altimetric changes, and then by multiply by the pixel size, we obtain the volume. In this case, let's use again the Sweet Creek landslide. By using this method, the total displacement surface volume is 2.6 times to the 7 cubic meters. How accurate is this value? I will say it's a very good guess, and is in the same order of magnitude as the one that was calculated in 1976 by a geotechnical company and by Mackenzie Johnson in 2002. And finally, let's look at the third result, the potential volume error introduced by altimetric variation. So as I mentioned before, we use the volume obtained with the interpolated pre-sliding digital elevation model and the 2006 LiDAR to obtain a volume. And then this volume is compared with the volume obtained with other altimetric surfaces that were calculated by a filtering process. In order to have an altimetric variation between 0 and about 2.5 meters. So let's look how the filtering process works over my interpolated pre-sliding surface. So we have first the post-sliding cross-section. Then we have in black line, we have my interpolated pre-sliding surface, which is my reference. And this surface is going to be filtered by using a low-pass filter. So we filter 5 times, 20 times, 35 times, 50 times, and 100 times. So as you can see, the effect of filtering make that the digital elevation model in the landslide area lose material at the headscarp and accumulate at the deposit. Now, how we relate these altimetric changes with the volumetric changes? To do that, we use the following table. So on the left side, we have the reference volume obtained with the 2006 LiDAR and the interpolated digital elevation model. And then we obtain the volume for filter 5, 20, 35, 50, and 100, and the percentage of variation of this volume. So for instance, for filter 5, the variation goes from 0 to about 6%. Now, let's relate it the elevation. So we use as a reference the interpolation digital elevation model as a reference. And now we use a technique that is called root mean square error. That this kind of error, we can thought as a kind of a normalized distance between my reference altimetry, which is the interpolated digital elevation model, and my prognostic digital elevation model for filter 5, for filter 20. So the difference between my reference and my predicted elevation for filter 5 is 0.24 meters. And the difference between my reference and the digital elevation model with filter 100 is 2.35 meters. So by using the root mean square error, now we can say that to the sub-meter level, the percentage of variation is going to be between 0 and about 17%. And above the meter, the error can reach above 170%. So that is the result of my project. Thank you very much. And if you have questions, I'm able to answer.
Okay, we have a question here. Is what was the resolution of LiDAR image?
Yeah, it was 3 meters for each pixel.
We have another question here. The overlay and the interpolation methods take into account the geomorphological changes for post-failure analysis.
No, actually, this analysis is like a black box because it was the scope of this project was to calculate the in a quick way the volume. If you need to do more precise study, you need to consider the topography inside of the landslide and also outside. But that is more specific work and it will take more time.
Okay. We have no more questions.
Well, thank you for inviting me.
Thank you very much, Dr. Gabriel. So we will take a break. 15 minutes to start with the other presentation. Dr. Gabriel, thank you very much. Bye-bye.
Bye-bye.
Hello, everybody. The following presentation is entitled Implementation of the Triggers Model with Reliability Analysis for Hazard Assessment of Shallow Rainfall Triggered Landslides. The author is Dr. Edwin Fabian Garcia Aristizabal. Welcome, Dr. Edwin.
Thank you, Alvaro. Good evening, everybody. My name is Edwin Garcia. Actually, I'm trainer professor at the University of Antioquia, Colombia. My research interest is related with landslides, especially physical modeling, couple modeling on saturated soils. And it's a pleasure for me today to present one of our research entitled Implementation of the Triggers Model with Reliability Analysis for Hazard Assessment of Shallow Rainfall Trigger Landslides. This work was developed together with Eddie Aristizabal, Roberto Marin, and Juan Carlos Guzman Martinez. As an outline of my presentation, firstly, I am going to introduce the topic of shallow landslides. After that, I will show some components of the triggers model, the methodology we use, coupling triggers with probabilistic analysis. And after that, I will present the deterministic results and the probabilistic result. Finally, I will conclude with some comments about the research. To begin, it is important to mention some mechanics and definition of the topics we are going to deal with in this presentation. Rain-triggered landslides, also called soil slips or shallow landslides, are mass movements with the plane of failure parallel to the slope, small thickness, we consider around 0.32 meters, no more than that. And also they have small scars. They are usually generated after intense or continuous rainfall events, but rapid increase in pore pressure or loss of apparent cohesion. It means reduction of suction or increase of the negative water pressure. Subsequently, the displacement mass by liquefaction or rapid reduction of the strength as in rain condition becomes a flow that propagates down a slope. Here we can see a picture that shows a little what is the behavior after infiltration of the soil, and we can see after saturation of the material, we can have a very parallel plane failure after infiltration process. This infiltration of trigger and landslides is very complex, and they have a lot of variables to be included. One of the main is the rainfall, the intensity and the duration, but also how the soil is capable to receive the water is very important. If the soil can receive the water, there is some reduction of the strength of the surface, and even the water can come into the soil and accumulate in the saturated soil. So we have an increase in the pore water pressure and a reduction of suction on the surface. So that's why it's necessary to implement a model that considers the infiltration process in the stability analysis. Here we have a picture, some pictures of some events related with shallow landslides. As you can see, these events are from small thickness, and they have very small scar area. Actually, the mass accumulation is due to the big number of landslides that we have, as we can see in the right picture. We can see many landslides, and after that we have a debris flow that can generate another problem or geological hazard. What is the idea of this research, or the main objective? We were thinking about susceptibility maps, which allow the identification of areas that are susceptible to landslides. So we can here see a picture of one municipality in which we employ the methodology, and we can see how we proceed in this study and how we can get the results. When we have susceptibility maps, we can take relevant measures to ensure disaster reduction. Also, we can offer safety to local residents, and with this, we can contribute to the formulation of territorial management plans in order to define some places for occupation. Let's go now to the triggers model. Triggers model is defined as the transient rainfall infiltration and grid-based regional slope stability analysis. We are going to see next some components of the model that we understand it could be very interesting to analyze problems related with rainfall triggered landslides. The program was developed by Baum et al., and it includes some information related with rainfall data, soil properties, topographical properties, and with one infiltration model, the program calculates the pore water pressure that can be positive or negative in order to introduce this information in a slope stability model to calculate a safety factor. Then triggers can develop a spatial and temporal distribution on rainfall-induced shallow landslides. This model has a hydrological component which is in charge to calculate the transient pore pressure changes due to the rainfall infiltration. This is very important. It means that I can calculate how is the volumetric water content within the soil during different steps or different times according to the rainfall is applied to the soil. This calculation can be made under partially saturated condition or partially or totally saturated condition. This is one of the advantages of the model. In this process, because the model is transient, and by using a simplified analytical solution of the Richard equations proposed by Srivastava, it is possible to calculate with the time of the rainfall how is changing the volumetric water content on the surface and how the water is accumulated in the saturated zone. So the program can calculate them positive and negative water pressures according to the distance I need from the surface. Also, from an initial pore water pressure with a rainfall and a function rainfall, I can determine in the program what is the variation of the pore water pressure according to the advance in time and the advance in the infiltration process due to the rainfall infiltration. Finally, to describe the exponential, the unsaturated between the negative water pressure and the volumetric water content, the program used a exponential hydraulic parametric model proposed by Gardner. It's a very simple model. It is made to make a linearization of the Richards equation. So it's possible to have some exponential function of the hydraulic conductivity and the volumetric water current to be implemented in the infiltration model. After this, finally, the program calculates how is the variation in the time of the safety factor, including positive or negative pore water pressure. This is one of the advantages. Is a model that can include both cases, in the case of saturation and the case of unsaturated soil, so the information can be calculated. Methodology. In our case, we use for one region in Colombia, in the Aburrá Valley, exactly in Medellin city. We use some information in order to make some susceptibility maps. Then we employ rainfall data. We use intensity, duration, and return period. We collect some geotechnical parameters, cohesion, friction, angle, and unit weight, hydraulic parameters, diffusivity, hydraulic conductivity, antecedent rainfall infiltration, and some geomorphological parameters as the dam, the flow direction, the slopes, and the soil depth. With this information, geotechnical parameters and hydraulic parameters, we generate some homogeneous geotechnical zones that I'm going to show later. The infiltration model is run, and after that, the stability model is applied in order to get a safety factor. However, as we get a lot of zones in geotechnical zoning, and this is a very huge area to be modeled, the parameters have some variation and uncertainty that is going to be considered in the analysis. Then with some information that we collect from the government agencies, from the geotechnical studies on the area and technical literature, we prepared some groups of parameters for the geotechnical zones and made a probabilistic analysis. This probabilistic analysis was run through the FOMS method. The FOMS method is first order second moment. And in this method, it is important to know that we can calculate a reliability index. In this reliability index is an idea, or it has a relation with the probability of failure of the mass I am analyzing. Based on this, we can see that if we have a group of parameters, we consider for the methodology that the distribution of the parameters is normal. In that sense, I have here deviation standard. If the deviation standard is larger, it means that the reliability index is lower. Then we hope that a high reliability index values result in lower failure probabilities. Then this is a way to account when uncertainty in the parameters, and the results, as you are going to see later, are much better to obtain susceptibility maps. The results. This is the results of the municipality of Envigado. We calculate using the triggers model, deterministic safety factors for a return period of 10 years, intensity and duration obtained from the intensity duration course from rain gauge located close to the area. And we get some parameters, some safety factors less than 1 and very close to 1 in some areas that are related with larger slopes. Also, we run the program for 100 years with a larger intensity. What we found here is that these zones with low safety factor are associated with the steep slopes. There is no big difference between the results of the two return periods. When we compare 10 and 100, there is no big difference, and this is due because the soils we are analyzing are soils with a low hydraulic conductivity. Then the water cannot infiltrate too much into the soil, so we don't have a large variation when we compare the results. On the other hand, we use the model and we apply the probabilistic analysis, introducing some variation in the cohesion, in the depth, and also in the friction angle. And with the same rainfall and same duration, we obtain the reliability indexes. As we can see here, we have another different result because we are taking the information, we are analyzing the information about hazard of the landslide, and we are seeing that the susceptibility map is showing a larger area because are including in the analysis some variation in the parameters. When we compare 10 to 100 years, there are no much difference, but the results from using the FOMS method show a more critical behavior in terms of stability than the results given by the safety factor. Obviously, because we are using some variation in the parameters. To conclude, I would like to mention the following. This methodology allows for a better representation of the process of rainwater infiltration into the soil. And it includes combined process of stationary and transient infiltration, especially the transient infiltration when we have large period of rainfall are very useful to analyze the topic of a landslide triggered by rainfall. And they are coupled an infinitive slope analysis that considers the effect of the loss of strength due to the infiltration process. This loss of strength in the program is also very interesting because it's not only undersaturated but under unsaturated conditions also. Triggers is a deterministic methodology. It is not a program prepared for doing probabilistic analysis but if you accompany this analysis by probabilistic analysis as FOMS, it's allowed to complement the results and to obtain critical failure areas depending on the triggering scenarios. However, it should be noted that FOMS method tend to be conservative model by assuming the behavior of the random variables and the safety factor using a normal distribution. This is a very simple model, so it is not possible to have different probability functions of the parameters we are using. Rain trigger and shallow landslide susceptibility analysis are decisive in defining land use in mountainous regions. This is especially in Colombia. We are working now very hard in defining the land use in many cities, so this is a very good tool to solve the problem. They can make a significant contribution to the land use planning. The models presented can be used as a landslide prediction tool as a part of early warning system. Some of the authors also are doing some exercises in applying these methodologies to early warning system. A limiting factor in the execution of this model is the lack of local study with the field data. We have large area of analysis, so we need a lot of parameters, but most of the time we don't have much information, or we have budget to do the field exploration. Then we need to get some parameters and to introduce the uncertainty of these parameters in the model. The models can be applied to other watershed as long as the thorough work is carried out through field campaigns for the acquisition of the soil parameter required by the program. Other type of analysis that can be carried out with this methodology are those involving assumed rainfall scenarios that induce mass models. This program can be useful to study how is going to be the problem of landslide associated with climate change. We have a large duration of the rainfall and large intensities, and how is this working and resulting in landslides over the time. This is my presentation. Thank you very much for your attention. This is my contact email. If you have any question or you have to give me any comment later, it was a pleasure to answer you. Thank you very much.
Thank you, Dr. Edwin. I have a question. Please go back to the first slide result.
Yeah.
Why do you, the second one, please, the next.
This one.
The other one, the next one.
This one.
Yes. Why do you choose that categorization of the hazard? Why the high hazard is classified less than the unity?
Well, okay, why I'm going to show this slide, this previous slide, and after that I go back. When we define the reliability in this, we can find that this index is calculated with the deterministic factor of safety. And we compare this value with 1, that is the limiting equilibrium of the soil. And we divide this by the distribution standard. Then if we have a value equal to 1, it means that the safety factor, the median safety factor, the average safety factor is very close to instability, and the high probability and the probability of failure is very large. Then we generate ranges between less than 1, meaning that the safety factor can be very close to 1, or even can be less than 1. And we say that this value is very close to 1 or less than 1 can be interpreted like hazard in a hazard map as very high probability of failure. When you take this value of reliability indices between 1 and 2.5, you are reducing the probability of failure, let's say 10%, 5%. So we consider that this is a medium hazard for landslides triggered by rainfall. And if this value is equal to 2.5, it means that the probability of failure is very low. We are reaching values close to 1%. Actually, I don't have now the relation between the probability of failure of the parameter. I forgot to put the table here, but this is the way we are going to control this. It means that the mean value of the safety factor is very close to 1, and when we take value of the reliability index larger than 2.5, it means that I'm very far from the equilibrium limit. I don't know if I could answer the question.
Yes, Yes, I have another question. The second
Yeah.
question is, why did you choose the first order second moment method? Why not Monte Carlo simulation or other reliability method?
The answer can be sound very simple because series is very simple method. It's easy to apply. It's only one equation. Compute time consuming is minimal. You have some assumption like the distribution is normal. It could be not true in soils, and it doesn't mean that this is much better than other methodology. No, you can use Monte Carlo, but as you know, in Monte Carlo, you need to run a lot of simulations. You can get very good results, but if you some repetitions in the calculations, it get a lot of time to obtain the results, and maybe this is not good. It is good if you have time, but if you are planning, for example, to use this information for early warning system, you need a rapid response of the program. If you have time, you can run Monte Carlo, for example, and you need you repeat 10,000 times the calculation. Here, you need to do this only 3 times. And with 3 times, I think you can get good results. So simplicity, low time consuming, this is the advantage of the methodology.
Okay, what is the main limitation of the coupling between triggers and the first order second moment method?
Limitation?
Yes, the main limitation of this coupling.
Yeah, actually, using the analysis time is not so much, increase just a little, but I think the main limitation is that you need to define very good the variation of the parameters, the deviation of the parameters, how you are sure or you ensure that the parameters represent the soil you are analyzing, because we are thinking about very large areas. We are taking here, we are analyzing 16 square kilometers. So this is a very large area, and to get very good geotechnical information for this area is quite complex. This is very difficult to be to reduce the uncertainty of the parameters. For me, this is the limitation. That's why I mentioned at the end that this is one of the drawbacks, not of the model. The model is good, the methodology is good, but to group or to collect the parameters for the analysis, especially geotechnical parameters, is very difficult.
Okay, there is no more questions. Thank you very much for your presentation.
Thank you again for your invitation. See you.
Okay.
Bye.
Bye-bye. Okay, we will take 10 minutes. We will be back in 10 minutes for the final presentation. Hello, everybody. The following presentation is entitled Debris Flow Mathematical Modeling. The author is the Dr. Mario Herman Trujillo Vela. Dr. Mario, welcome.
Thank you. So this is a work that we have been performed in collaboration with Professor Alfonso Ramos, Jorge Escobar, and Sergio Galindo Torres. And I have done this based on the study of debris flows that have been performing for 10 years. And the last part I developed in Westlake University in China. So I want to start with the motivation. So sometimes it's not that easy to choose a model to represent debris flows, and this is very important because it helps us to better understand how these kind of flows will move and where, what areas can be destroyed and so on. And for example, these two photographies are showing a top view of two big events that occur in Colombia. The first one it's Alahar that occurred in Armero in 1985. And the second one was 5 years ago that occurred in Mocoa. And so debris flows are mixtures of soil and water, and they are going down slopes and streams driven by gravity, and they are generated by two main aspects, let's say. The first one is the ground's mechanical state. So for example, it can be measured by some variables: friction angle, cohesion, for pressure, for water pressure, and some external forcings. So for example, rainfall, volcanic activity, glacier melting, and anthropic activities, and so on. And also they can carry everything that they found they can find in their path. So logs, big boulders, very small grains, clay, etc. So there are, like in other natural phenomena, there are three ways to study this kind of natural events. So the first one is field observations and measurements. The second one is physical models at the laboratory scale. So, for example, the figure on the right-hand side is showing a flume 100 meters length, and that experiment have been performed at the U.S. Geological Survey, and they have collected the data of many debris flows experiments in that flume, performed in that flume. So how to represent the debris flows? So natural phenomena in general can be conceptualized and expressed using mathematical formalism, or concatenating mathematical expressions with physical laws. So this is necessary to be said because not only physical laws are employed to model debris flows, but other, let's say, simpler mathematical rules can be employed to try to study this kind of phenomena, but not from the physics. So, but both are employed, and this work have been based on the physical based models. So there are many mathematical models that can be found in the literature, but sometimes it's not that easy to find what models to select, or under which aspects or parameters to choose a model. So what we wanted to do here is to set up the main aspects must be taken into account to model a debris flow. So the first one is phases. So as you can find in the literature, there are many models that can be single phase, mixture models, and multi-phase models that can account for more than one phase. Let's say water and soil. And another very important aspect is entrainment. Debris flows can drag material from the bottom and from the banks, from the lateral banks. So this is a very important aspect because it can increase the initial mass a lot. And then the other one is constitutive relationships, which are describing the behavior of the mass while going down the stream or the hill. And spatial dimensionality. So we have three-dimensional models, two-dimensional depth average models, and one-dimensional depth average models. And the last aspect that is very important is how to solve all the set of equations that are describing debris flows. So, for instance, we have here a three-dimensional multi-phase model, and where equation one, or this first equation, is showing the mass conservation, and so the first term is showing the change of mass regarding time, and the second one with respect to the space. And this is equals to this E, which represents the entrainment rate. So this is the term that will describe how the mass is entrained to the main flow when lateral banks and bottom are eroded. And then we have the momentum conservation equation. And something that is important to show here is that the terms on the right-hand side are showing all the forces. So gravity force, that is the first term, and the right-hand side. And the second one is showing pretty much the stress tensor, which is describing the behavior of the mass. So this will be replaced with the constitutive model. The third term, F, is representing the interaction forces between phases when a multi-phase model is employed. And the last term, that is the momentum production term, due to the mass that it was recently added due to the erosion of the banks and bottom. So in the same way, there is mass added into the main flow, there must be momentum added into the main flow. Then we have the mixture models, and they are weighting averaging variables. So, for example, the density, which is rho, or the momentum, which is rho by u, or by the velocity vector. And the same for the stress tensor, no? So we are multiplying the, let's say, the stress tensor by the volume fraction, which is alpha. So in this case for the soil, and plus the volume fraction of the fluid by the stress tensor of fluid. And we can have a single phase model is just if we just suppress the tilde. And so the entrainment rate, it's it's a kind of relationship between the ground, let's say, or the colluvial fan and debris flow. So they are bringing more material from one point to another, and then this material is deposited and in a specific place when where the gradient slope is very low, and then in other events this material can be dragged again. So the material is like kind of recirculating from the ground, let's say, and from some points to another. And yeah, there is that kind of relationship there. And so the way to describe that is there must be an equation that describes how the bottom or the surface is changing, which is given by this Exner equation, this simplified Exner equation, and which is equal. It's the variation of the bed or the topography, let's say, which is B with respect time equals minus the entrainment rate. So in this entrainment rate, there are many formulas to describe this. Let's say one typical way to describe this entrainment rate, from those ones that tend to be more physical based, is it must be a function between the difference of two shear stresses. So one is the shear stress given by the main flow, and the other one is the shear stress given by the bottom. And so there is this another equation that was developed by Professor Pudasaini to correct or better handle the momentum production when let's say new mass is added to the main flow. Another important aspect is the constitutive relationships. So this is one of the widest topics in debris flows, I will say. So for each kind of material, there is a constitutive relationship, the rheological model. So for instance, for soils, you can find perfectly plastic models, elastic perfectly plastic, elastic viscoplastic, viscose perfectly plastic, hypoplastic, and new rheology. That is, it's a kind of new kind of rheological models. And also for fluids, so we need constitutive relationship for the volumetric part and for the deviatoric part. So for the volumetric part, we need expressions to compute or to obtain the pressure. And for the deviatoric part, it's the one that is related to the viscosity. So there is always a relationship that is describing the viscosity of the main flow and how this viscosity is taking off kinetic energy from the main flow. And then we have interaction forces, where we also have the volumetric part, or the volumetric interaction forces there between, let's say, fluid and soil or the solid particles. And also we have the deviatory component. And then we might have linear drag, nonlinear drag, and even another term that is called usually virtual mass. So from the soil standpoint or soil rheology, so as I mentioned before, there are many relationships, and a specific way to represent. Sorry, I will put this here. And a specific way to represent this kind of equations is we have sigma prime sub s, which is equal to a function of the strain tensor and the stress tensor of the soil. And in this way, then the basic way to write the elastic, and I just put 3 points there to say any kind of model which is also elastic. So let's say elastic viscoplastic or just elastic perfectly plastic or elastoplastic model. So can be written in this way, and it depends. It will change mainly how this strain tensor will be accounted. So if this is plastic or viscoplastic and so on. And we have also hypoplastic models, which are accounting for expressions that are relating the stress tensor of the soil and the strain tensor in a linear and non-linear way. And also rheology, it's another kind of rheology, which it's accounting more for granular flows, where the inertial force it's very important. So this is another kind of models that have been more recently developed for granular flows. So we have in this figure the representation of some of these models to have an idea how they will behave in a general way. Then we have fluid rheology. So the general equation to describe a fluid is this one. The stress tensor of a fluid is equal to minus pressure plus the shear stress tensor. And that shear stress tensor, it can be also written in a general way as in equation 13. And then we have, let's say, a GL stress, which is tau 0 plus 2 nu, which is representing the viscosity. And that also this viscosity might be not constant, non-linear, and also might depend on the strain rate tensor, by the strain rate tensor. And this n is called the power index. And as these three parameters, so the GL stress, so tau 0 and nu or the viscosity and the power law index are selected, then we can have different models, no? So we have a Newtonian model if tau is 0, tau 0 equals 0, and the viscosity is constant, and the power law in the index is 1. And then if we change these parameters, they will have Bingham model and the power law models, which is this Ostwald, and then Herschel-Buckley also. And alpha rheology, this is another kind of models to account for non-Newtonian fluids, where we have a strain rate tensor, which depends on the volumetric solid concentration, no? Which is this alpha S. And then also we have a graphic here, which is showing just in a general way the behavior of some of these models that are employed in debris flows. So we have Newtonian, Bingham, Herschel-Buckley, the power law. This is more for explaining the non-Newtonian models here, and also, well, other ones that are more employed for debris flows are Pagnol, Bingham, Papanastasios, very common, and Shaw. And also we can see changing based on the yes, as a function of the shear strain. Regarding pressure, there are many ways also to handle the pressure. So the first one and the most difficult one is the pressure. Then solve to obtain the pressure solution of the momentum equation. Then another kind of equation is to use a kind of a kind of equation of state. And the equation 17. So this one is more a physical based on waves. And this one is more empirical one, but both have been employed to model debris flows. And the most common one, which is the hydrostatic pressure, and especially with a correction, no? So that is in most of the new papers, especially, there is always a correction factor, let's say, there to correct that hydrostatic pressure. This can be, for instance, adding an extra, let's say, acceleration, gravitational acceleration, as can be seen in a paper from Iverson, and others are based on a formulation that represents the excess of fluid pore pressure in the skeleton of the soil, and other ways you can find the literature. This is the phase interaction forces. So usually we have Terzaghi-Effective stress to link two phases. To link the volumetric part of two components, no, which is usually soil and water. And then also we have the deviatoric component. So equation 22 is showing a Forheimer equation in addition to an acceleration term. So the first term on the right-hand side of equation 22 is just Darcy law, and then if we have the two components, the first two components, we have the Forheimer equation, which is a nonlinear equation or nonlinear term, which is the second one, and then we have the third term, which is accounting for the acceleration of let's say when there is an acceleration of a particle, and then this is affecting the surrounding fluid. So this term is accounted for representing more that effect, and it is possible to find different ways to link the deviatoric component of the interaction force between different phases. No, so some papers are using just Darcy law, other papers are using just the nonlinear part, and others are using the last two terms. No, that is nonlinear and the acceleration term. And another aspect is spatial dimensionality. So one more time, we have the conservation equations, mass and momentum. And after depth integrating the model, or depth averaging the model, we have reduced the equation. So we have one less term, which is the C term in this case. So there is no term with respect to C, and in the same for the momentum equation. No, there is not a third momentum equation. There are only two. And another important aspect is age. So in compensation of losing this third momentum equation, for example, then we are having a new variable, which is flow depth, which is represented by h. And then the other variables are average in depth, no? And then this is denoted by the bar over the velocity, for example. And the terms on the right-hand side are the sources terms. So again, gravity, the stress tensor, the interaction forces, if this is multi-phase, and the total momentum or net momentum production term, if this is regarding to the entrainment rate, no? If there is entrainment in the main flow. And finally, the solution methods. So we have many solution methods to solve the partial differential equations. We have to solve to represent debris flows. So if we reduce the equations, sometimes we can have analytical solutions using some of these analytical methods. For example, the method of characteristics or separation of variables, which is one of the most common ones. And there are also some other kind of solutions that are called similarity solutions. And this is a very new method that is called least symmetry. So it's a method that has been recently employed by Professor Kudasaini. And then from the numerical standpoint, just being focused on the space discretization. Regarding to the mesh-based methods, we have finite difference method, finite element, finite volumes, and the in some spectral methods that are discontinuous Galerkin, and another one that we have employed to solve this kind of equation that is called spectral multi-domain penalty method. And from the mesh-free methods, we have also mainly two methods, which is discrete element method and smooth particle hydrodynamics. You know? So these two are fully mesh-free methods that have been employed to represent the flows. So this is a scheme that is showing how these methods in a general way are performing the space partition. So we have two kind of mechanics. So even we can have a third one here, but it's not here. So from the mechanical standpoint, we can have the continuum and let's say discrete mechanics. And also, I could draw another one that must be statistical mechanics, which is the base of Lattice-Boltzmann. So that's the base, no, the base part of this method. And then we have the approach. So it can be Eulerian. So we have a cell, and then we can see how the variables or how the mass is crossing this specific cell, and then how the variables are changing as the mass is crossing. And also the other approach is the Lagrangian. So in this case, the mass is moving with the grid, no, or the points. So there are grid in the case in the case we have a grid. So the grid must be distorted, and then it must move with the mass. And in the case we have points, it's the same story. So the points will move, carry on the variables and everything there, no? And also then the discrete, which is pretty much the scheme in let's say in row D is showing discrete element method, no? It's very discretized particles are representing the whole mass, and then they are interacting as different individuals, let's say. And then how the space partition is performed. So mesh-based and mesh-free methods, no? So in mesh-free methods, we have points or particles that are moving, carrying on all the variables with them, and then interacting with the neighboring points or particles. And the mesh-based methods, there is a mesh, and then the mesh must be distorted in the case of Lagrangian, or the variables and the properties are crossing a cell, and then we can see what is happening there. And then how to choose a model. So this would be started with this scheme. So this is placing 4 regimen flows of debris flows, let's say. So we have the regimens for fluids on the bottom of this figure, and the regimen of the soil on the top, and the quasi-static states of both fluid and soil are on the left-hand side, and the inertial regimen of these two components, so fluid and soil, are on the right-hand side. And then we have like the basic forces that employed to represent each regime. So inertial soil, fluid, quasi-static fluid, and quasi-static soil can be expressed or represented by these basic, let's say, constitutive equations. And the relationship that we can have between these different constitutive relationships, then we can have some dimensionless numbers. So, for instance, we have the friction number, which is NF, and the Savage number, which is NS, the mass number, NM, the Reynolds number, and also Bagnol's number, which is NB now. And then, sorry, and then the way to select if we can use a single phase model or a multi-phase model might be led by this number, by the mass number. So, for instance, if the mass number is lower than 1, fluid momentum dominates the flow. If the mass number is greater or equal than 1, then the soil momentum will govern the process. No, it's the soil component will be more important. And then if the mass number tends to 1, then the momentum contribution is similarly influential from these two phases. So both fluid and soil will be very important. So if both are contributing in that way, in a similar way, so it might be possible to say that multi-phase models are needed there. And otherwise, if the mass number is diverging from 1, as you see, it's to say it's lower or greater than 1, then probably single phase are not bad choices. But what is important also to say here, it's the volumetric fraction of each phase is changing with respect to time and space. So this must be carefully be taken and analyzed to see if it's really possible to simulate, let's say, a dry granular flow or just as a fluid. So it depends from the case. And also we have the entrainment of materials. So one number that might help us to decide about this is the entrainment ratio, which is the relationship between the entrained volume into the main flow and the initial volume. So Aldrich and Evans are saying that if the entrainment ratio is greater than 0.25, then the entrainment must be taken into account in the mass and momentum equations. No, so there are some models that are representing the entrainment just by the mass conservation equation, but this is not correct. It must be by both equations, mass and momentum equation. And also, there is another recently developed number that is called mobility scaling, developed by Professor Pudasaini, and this is a nonlinear relationship between the erosion induced force and the net driving force of the mass. So the erosion-induced force is represented by Pm, and this is a function of a drift factor, and which can be checked in Professor Kudasaini papers. And the other term is its M, which is the net driving force. It's all the forces, or pretty much the most important forces that are acting on the main flow are enclosed by this term, by M. And so if we have the erosion-induced force, so Pm equals 0, then Sm, or the mobility scaling factor, equals 1. So this means there is no erosion caused by the flowing mass. And also, if the erosion-induced force is greater than 0, then the mobility scaling is greater than this means the mobility, or the run-out distance, will be greater. In the case we have these two parameters. And if this means we more mass, we more mass in the main flow, but it doesn't mean always it will be longer. There will be a longer run out distance, so it can be also reduced even if we have new entrained mass. And regarding the horology, mainly two numbers might help us with this, which is one is the friction number. So if the friction number is greater than 100, we have a quasi-static frictional regimen. So it's more important the friction that the grains are having there, and then they are dissipating the greater part of the energy. And if the friction number is lower than 100, so the viscous forces are more important. And the other one is Bagnall's number. And so if we have a Bagnall number greater than 200, the inertial forces of soil, one more time, are very important. And if this is lower than 200, so the viscous forces are dominating the flow. So this might give us an idea of which kind of models to choose, which rheological models. For example, if we are in a quasi-static frictional grains, then let's say Morculum, and Ducker-Prager, and all these kind of models for soils might be more appropriate, though. And whereas if we have a Bagnall number greater than 200, maybe new rheology can be more appropriate, no? Because there is an important part of the inertial grains playing a role there. And in the opposite, if we have a friction number lower than 100 or a Bagnall number lower than 200, then rheological models related to fluid will be more appropriate. Spatial dimensionality, so there are some important things also here, and three-dimensional models are mostly employed for laboratory scale experiments. Two-dimensional plane strain models are indicating that they are laterally constrained, and then we have a main direction for the flow. And for this, we also can use a sinuosity index. So if we are analyzing like a very straight flume or a very straight part of a natural, let's say, stream, and then we might apply this kind of models, no? And this sinuosity index, if the sinuosity index equals 1, so that means the flume or the stream is straight. And if this is greater than 1.1, the current or the flume will be considered sinuous already. So this cannot be appropriate if the sinuosity index is greater than 1.1. And then we have two-dimensional depth average models, where we are saying pretty much with this one that the vertical things that, or the things that are occurring in the vertical direction or in the flow direction are not important. And well, this is a very well-known number for this that must be employed, which is the aspect ratio, which is taken the maximum height of the flow from the highest point to the lower point over the length or the distance between these 2 points, no? And this must be much lower than 1. And also, this is something that is very important here, as this model has initially hydrostatic pressure, so this must be corrected for steep slopes. And is the same story for one-dimensional depth average models, no? And one more time, apart from the aspect ratio and the pressure, the correction for the pressure, the sinuosity must be taken into account, no? Because one more time, we will do it for lateral constrained flow if we are assuming that this is one-dimensional. And solution methods. Analytical solutions are important, are for idealized cases, and are important for performing preliminary debris flow hazard analysis, quantifying the error of numerical techniques, and validating new computational tools. In numerical solutions, there are 4 aspects that are important when choosing numerical methods or a software or an open source code, which is computational resources. So if we have, let's say, good computers, and we can have parallel codes there and perform quick solutions with these supercomputers, let's say. Software availability, so maybe we have very good models but no available software. So accuracy. So there are many numerical methods. Each method has a different accuracy, and it's very difficult to take into account, no? And the versatility of the code to be modified or coupled. And so this is just a little part of the table we have in the paper. So it's just summarizing all these models, some of the most important models. And we have, importantly here, we have all the aspects, or we have summarized all the aspects we have been talking through the paper. And we have also available software here. So regarding to each mathematical model, no? So there are many codes that some are available, some no, other ones you have to pay for them, and so on. And that's all. Thank you very much.
Dr. Mario, thank you very much. I have here 3 questions. The first question is, what is the most efficient model in terms of accuracy to represent the debris flow?
There are, regarding numerical techniques, there are some models that are liked by scientists, which is shock capturing methods. So even if you have a finite difference method or volume methods, there are some extra, let's say, extra treatments can be seen from that standpoint that might help these methods to better reproduce these continuities. And these methods are usually called like shock capturing methods. Because yeah, they have been created to better represent these continuities. So, but yeah, this is very better always corroborated using or quantifying the error, no, or each technique using the benchmark cases and so on. So it's not that easy to really say which is the best one. So it depends from the problem, from the questions, and so on. So it's not very easy. But these ones are very common. The shock capturing ones are quite common.
So what is the most used model in the literature?
The most used model for what?
What is the most used model in the literature?
Well, the software developed by Professor Pudasaini is gaining importance. No, I think there are some papers lately published also with applied cases there. So likely this one, but through time, also flow 2D, which is it's pretty much having the O'Brien and Julian thinking in rheology, no? And the other one thinking in area flow, which is the one developed by the laboratory of Professor Pudasaini. He's using, yeah, his own equations and develop models and rheology and so on. No, based on previous, but no very widely used questions.
Okay. The third question is, what models have been validated for application in Colombia?
I think maybe this O'Brien and Julian is one of the most employed ones, no? But yeah, likely this one. But the new models are starting to be more and more employed, no? As the practitioners and scientists start to have these other models, and we have maybe more options with the computers, because yeah, we have very better computers nowadays, so it's easier to run a little bit more complex models, no? Maybe this one is more employed here also in Colombia.
Okay, thank you very much. There is no more questions. It's all.
Okay. So thank you very much for inviting me.
Thank you very much for assisting.
Okay.
Bye-bye.
Bye-bye.
Okay, we will be back in 5 minutes with the final presentation. Hello, everybody. The following presentation is entitled Debris Flows Occurrence in the Semi-Arid Central Andes, Subtropical Andes, under Climate Change Scenario. The author is Estella Modelas. Welcome, Estella.
Welcome. Thank you. Thank you for your presentation. I'm Estella Moreiras. I'm from Argentina. I am a researcher and professor of the University of Cuyo. I'm hoping that we have a good communication. You can hear me well during this talk. Well, I'm going to present some advances in a review paper that we published in Geoscience the last year about debris flow in the Andes. We try to gather all the information about debris flow in this region because 96% of fatality are triggered by precipitation, and if we see a fatal landslide, at least 73% of fatal landslide are triggered by precipitations. So we concentrate in the arid central Andes of Chile, Argentina, between 30 to 34 degree south latitude, and this area comprises the western slope of the Andes that are Chile, and the eastern slope are Argentina, and the area comprises the highest peak of the Andes, Aconcagua Mount, with 6,958 meters above sea level, and we have different geological units along these Andes that we have main cordillera, frontal cordillera, and precordillera. So we have different kinds of rock in this portion of the Andes that comprise the Mendoza city to the east and Santiago to the west. So in this region that fall in the arid diagonal segment, the precipitation are related or forced by the behavior of the ITC zone. When this belt go to the north during winter, we have all the humidity that came from the west, from the Pacific anticyclone, and would call westerlies, and all this rainfall affect the Andes region. And during summer, when the ITC zone go down to the south, we receive all the precipitation from the Atlantic anticyclone. If we made a profile, this is a chart from Viale this year in the paper from Frontier. We can see a profile, the elevation of the Andes. This profile is for this latitude, 30 to 32, and this profile is to the south, 32, 34. We can see all the meteorological stations, and the rainfall, the winter rainfall that we receive at this latitude is really very low, 400 millimeters as mean annual precipitation. And to the south, this precipitation increase. We are talking about winter precipitation, the precipitation that we receive from the Pacific anticyclone. We have at least 1,000 millimeters in the western side, and this rainfall is lower to the eastern part of the Andes. So in this scenario, we have the climate is also forced, or precipitation are forced by the ENSO, the warm phase of the ENSO, El Niño, and also the PTO. Here in this illustration, this figure, we can see a large drought that has been affected the area during the last 10 years, with 30% less of rainfall that have generated a lot of fires in the region. And we can see in In brown color, those affected vegetation, no healthy vegetation, and in light blue, a good health of vegetation. So in this region, we have a very contrasted environment. We have a very high topography. We have area that receive high precipitation and other areas that are very arid, particularly in the higher part of the mountain. We have also a different temperature, the higher temperature and the lower part, and the color or less temperature in the upper part of the mountain. And also we have different kind of glacier. We have covered and uncovered glacier in this area. And that's important to understand the permafrost and pre-glacial areas of this region. So in this area, we are going to have different kind of debris flow. Normally, these debris flow are generated in very steep slope. They are associated to a stream flow, river, and alluvial fund. As we can see in this chart of Galmont of 1956, we can see that we can have mud flow, debris flow, but also we have hyperconcentrate flow associated to a stream flow. So in the nature, we are going to have all kind of debris flow that can be mixed in the river or in the alluvial fund. Also, we can have hyperconcentrate flow associated to glacial outwards flows and landslide damaged lake overflow. This is a map of the historical event that we could gather from the study area. And as you can see, all these historical events are concentrated along the road where somebody has reported this event that has generated some damage to the road or to some village. Yes, generally the damage are associated to national or international road. So we have at least 400 historical events. So from this event, we can have some data. Normally, the person or the institution reported the damage event, but they don't estimate or don't have information about the velocity or the volume of this event. So when the data could be recovered, we can calculate the relation between here the volume in this graph and the runout. We can see some event, for example, in the Chilean part. This triangle is related to the Parraguirre event in the Colorado River that was generated in the glacier area. So we have some snow or ice incorporation in this event, the same that the event that occurred in Juncal Glacier. So they really have a long run out or a great distance, but the great distance are found for the Glove event that are related to the collapse of the ice damming lake. And this event was also a rupture of natural dam that was generated in San Juan in Argentina. This is the event that present the higher runout, but the volume was not so big as those recording for Glove event. In this part, this rectangle represent this data. We have the more common debris flow that has been recorded in the area, that as you can see, they move or they take a distance of 9 kilometers until 10 kilometers, no more, and the volume don't reach 1,000 cubic meters. But really, the volume are really important to the road and the infrastructures affected by this debris flow. And in this chart, we can reconstruct relation between mean velocity and the runout. And really, we couldn't find a lot of data about velocity, but here there are an inverse relation between runout and velocity. We also reconstruct some spatial distribution inventory map about historical and also event of debris flow. This map is from the Mendoza River Valley in Argentina, and we estimate the mean annual precipitation, the precipitation to generate landslide at Regis value. We found that normally the number of events are related to those areas affected by El Enso, but the warm phase of the Enso phenomena. And the precipitation for generate this debris flow are really low. We have debris flow when the precipitation is 7 to 10% of mean annual precipitation. We are going to have at least 50% of our debris flow has been generated by this low precipitation. Also, we have had debris flow generated by permafrost melting. Here there is some cases near Aconcagua Park. This is from Aconcagua Park, Los Grises Galley. This is also debris flow generated in the Aconcagua Park. This is La Salada Galley, and this is El Negro. That all these events were generated in the summer of 2015 and 2016, between December to January. Here is represented different belt, different color represent the altitude. These are the date, and the blue dot represent the altitude of the zero isotherm. We can see that the line, the blue lines and this line represent the event. And here we can see the increasing of the altitude of the zero isotherm and then the occurrence of this event. At least 4 events were recorded in this galley the day following the increase or the climbing of the zero isotherm. In this galley, we can find a rock glacier that the frontal part of this rock glacier falls during the melting of the permafrost. Also in the Negro Galley, we found also an increase of the elevation of the zero isotherm, and also we record 3 events after this episode. And finally, in the Soltera Galley, we also found an increase of the zero isotherm, but this event was also generated by precipitation. So there are 2 causes from this event in this galley. Also, we have found some debris flow generated by permafrost melting in Elqui Valley. In this sector, we couldn't find any record of precipitation. Here we estimate Vergara, estimate the permafrost distribution, and estimate the potential solar radiation. And in this area, also we can find record from the neighbors meteorological station, and we found that was an increase in all of them of the temperature associated to the debris flow generation. So in this area, we have both an increase of temperatures and permafrost degradation associated to this debris flow. When we are talking about temperature, also we can see that with the temperature, we condition the kind of debris flow that we are going to have. With higher temperature and higher storm precipitation, we are going to generate debris flow and mud flow, or we have a greater probability to generate debris flow and mud flow. And with lower temperature and lower precipitation, it's more probably to generate hyperconcentrate flow. So if we see our study area, we can find that we have some events generating in the upper part of mountain area. Here is a profile in the Mendoza River Valley. Here is main Cordillera. This sector is frontal Cordillera, and this part is pre-Cordillera. We have some events generated in this sector. At least 16% has been generated by thawing or permafrost degradation. In the lower part of frontal Cordillera, we have those debris flow generated by rainfall, and this rainfall normally came from the Pacific, so they are associated to the westerlies. And in the lower part of the Andes, in pre-Cordillera region, we have debris flow, but this debris flow are generated by rainfall that came from the eastern part, from the Atlantic anticyclone. So in this area, we have different triggering of the debris flow or high discard flow. So for ending on to remark our result on this paper, we found a higher temperature, the elevation or climbing of zero isotherm, the permafrost degradation, the intensification of the ENSO, and concentrate episode of heavy rain are affecting the slope instability in this portion of the Andes. So thank you for your attention.
Thank you. Thank you so much. It was wonderful, this presentation. We are very happy that we could finally hear your knowledge or what you had for us. And thank you for being here, even though any confusion that it wasn't expected, but we finally could hear you. Let me see if we have any questions. I am here looking at the chat in YouTube. I think we don't have questions here. So if anyone have any question, you can write it right now. Then I just want to acknowledge Dr. Estella Modelas. Thank you so much for being here. And thank you, all of you who attended this, I think, almost, I am checking right now here in YouTube, almost 10 hours of the live streaming. We today had wonderful presentations. We learned a lot. We had a discussion section. We could talk with other researchers, and all right. This is the end of this day. I don't know if Stella wants to say something to say goodbye.
No, thank you. Thank you for inviting me to give this presentation. And sorry for the misunderstanding about the time, the correct time. So I hope that the communication has been okay, because we have problems here in Argentina. We have a storm, and really everything was collapsed.
All right, no problem. All right, thank you so much, and goodbye. See you tomorrow in the last day of the Landslide Scientific Assessment Conference. Bye. Goodbye.
Okay, thank you.